CI related to lithium-ion battery, supercapacitor, and then lithium-ion capacitors. So this slide shows that various energy resources available for that the generation of energy, and then statistics about the global energy consumption. As seen in that the pie chart, the coal, natural gas, and then oil. These three fossil fuel contribute the major energy sources like 34, 21, and 25%. So, and then the more important thing, even though now we are generating energy from these fossil fuels, if you can see that these fossil fuels available only for limited periods of time. For example, that oil, it will be available for only 30 years, and then natural gas and then coal available only for limited period of time. But if you can see the energy requirement right now, it is 13 to 15 terawatt per year. So if we estimate that the energy requirement for 2050, it is about 30 terawatt. So another issue when we are using this fossil fuel for energy generation is it emits a lot of CO2 into that environment, which leads to the global warming and the climate change. A lot of things are happening because of this CO2, more CO2 into the atmosphere. So the major two things which motivate us to move that from fuel-based vehicle to the electric vehicle is one is the depletion of fossil fuel and then large CO2 emission because of that the fuel which is used in the transportation sector, which is cost nearly 15%, nearly 16% emission. It is coming from that the road transportation. So this slide shows that what are all the other energy sources available for that the generate to meet our energy demands. If you can see that the solar and then wind, these are all the natural sources which is available for that energy generation. So we can generate energy from these natural sources. Where will we store this energy? So for that aspect, the lithium-ion battery supercapacitor are the two important energy storage system. So to store the energy from that renewable sources. For example, lithium-ion batteries, it stores energy through that electrochemical redox reaction, whereas the supercapacitor, it stores the energy through that the electrostatic absorptions of the electrolyte ions. So I'll be talking the developmental activities later. Before that, I would like to give that brief introduction about the lithium-ion batteries. What are the batteries? A battery is a transducer which converts the chemical energy of its active material into electric energy via that electrochemical redox reaction. There are two batteries available. One is non-rechargeable, which is called primary. Another one is rechargeable battery, which is called the secondary battery. So any battery, if you take it, these are all the four important components of the battery. One is the anode negative electrode, which mostly graphite used as an anode material, and then the cathode, which is called the positive electrode. Mostly the lithium-based compounds are used as a cathode material in lithium-ion battery. So the third important component is electrolyte. So usually lithium salt, the commercial lithium-ion battery having lithium hexafluorophosphate dissolved in ethylene carbonate. So diethyl carbonate used as an electrolyte, and then the separator, which avoids the short circuit between the positive and the negative electrode. Usually the porous polyolefin, the polymer used as a separator. So the right hand side, if you can see that these are all that existing cathode and then anode material which are used in the commercial lithium-ion battery applications. So always, if you can see that the cathode materials having the higher voltage and the anode material having that lower voltage. So when you choose that the higher voltage of cathode and the lower voltage of the anode, you will end up with a high voltage of that cell. So which increases the energy density of your cell as well as the capacity. So you may ask, what is that the advantage of lithium-ion battery over the existing other secondary batteries available in the market? As you know, there are the secondary battery like nickel cadmium, lead acid, alkaline, nickel metal hydride, all these secondary batteries available in the market. How that lithium-ion battery is having advantages over these battery technology. If you can see that the table, the energy density of lithium-ion battery much higher than the other nickel cadmium and lead acid battery. It is about 150 to now that the energy density is about 250 watt-hour per kg, whereas lead acid battery it can deliver only 30 to 40 watt-hour per kg. And then if you can see why energy density is high, because the voltage is high. You can go up to 4 voltage when you use lithium-ion battery, whereas if you see the other secondary battery, it is less than 2. That is the reason the energy density is lower in the other secondary batteries. And then if you can see the cycle life, it can go up to 10,000 cycles. And then the power delivery also, it is moderate. These are all the advantage makes that lithium-ion battery better than the other existing secondary batteries. This slide shows that the history of lithium-ion battery. So the first lithium-ion battery, it was invented in 1976 by Professor Whittingham. So he developed lithium titanium sulfide as a cathode and then anode, lithium foil as a anode material. First lithium-ion battery, it was invented in 1976. In the later 1980, Professor Goodenough, what he has done, the lithium titanium sulfide, which was developed by Professor Whittingham, that voltage is only 2.5. What he has done, he has developed that layered structure called lithium cobalt oxide, which can go up to 3.7 volt. So he replaced that the lower voltage cathode with the higher voltage cathode. Still, he uses lithium foil as an anode material. So later, the Japanese group led by Professor Yoshino, they have replaced lithium metal with the graphite as an anode material. With this combination of lithium cobalt oxide as a cathode, lithium this graphite as a anode, this first commercial battery, it was introduced by Sony in 1991. So the research, it was started. The first battery, it was invented in 1976, but the lithium-ion battery comes into the market in 1991. This many years it takes to take that technology into the commercial market. So later, many that other advanced battery technology has been developed using that various other material called lithium, nickel manganese cobalt oxide called NMC, as well as nickel cobalt aluminum oxide, which is called NCA. So with this combination, Tesla battery and all, they are using NCA as a cathode and then graphite with the silicon as the anode material, which is giving that high energy density. So because of this, the invention, now the lithium-ion battery is available in the commercial market for various applications. By recognizing their effort, last year, all these three gentlemen, they awarded Nobel Prize for the chemistry in 2019. So this slide, I would like to give that what is the mechanism for that when you are doing the charging of lithium-ion battery, when you are doing discharging, what is the actual mechanism involved in that? As I told you earlier, lithium-ion battery having the components of cathode, anode, and then in between the separator to avoid the short circuit between the positive and the negative, and then the electrolyte, which is the ionically conductive, electronically so not conductive. So the current collector, which conduct that electron to the external lobe. So this is the typical component involved in that lithium-ion battery. So when you are connecting your plug into the power system, what happens? This is that the cathode, usually lithium-based compound. When you are doing charging, there is a oxidation occurs at that the positive electrode. So lithium electrons, it generates lithium is coming through the separator and intercalating into the anode, and whereas the electron goes to the external circuit and charge your system. How you can make it fast charging? Based on this mechanism, you can see that. So when during oxidation, there is lithium ion as well as electron. So if you have that nano-sized particle, your diffusion, it will be very faster from that cathode to anode. And then if you have that good conductive medium, whatever the electron generated within that the crystal, it will diffuse through that the current collector, and it goes to the external node for charging your devices. So this way it is important. Nano size cathode material and then good conductive medium are essential to increase the diffusion kinetics of lithium ions and the electron which is generated during the oxidation. By doing this, you can increase the efficiency of your lithium ion battery. So exactly the reverse thing happened when you are doing that discharging. This is what it happened. Whatever the lithium ion it is integrated into the anode, it goes back to the cathode material, and the electrons from the anode it goes to your device for functioning of anything, electric vehicle or mobile phone or whatever the devices. So it will be used. This is the simple mechanism involved in that lithium ion battery. So you have to play with that, what kind of material I record, what kind of application I'm preparing that material. Those aspects, you can tune the parameters and then you can prepare the material according to the requirement. So this slide shows the application of lithium-ion battery for the portable electronics as well as the electric vehicle application. So now that it is lithium-ion battery is very attractive for that the electric vehicle application. So these slides give that the what is the importance of the electric vehicle compared to that fuel-based vehicle. So how it functions, that the electric vehicle, the vehicle which is propelled by an electric motor. There is an electric motor which is powered by a rechargeable battery pack called lithium-ion battery or lead-acid battery. So even Varanasi and all, they are using that lead-acid battery powered e-rickshaw. So your battery pack, it is connected to the electric motor that is running your electric vehicle. As I mentioned, all these things, change of climate due to greenhouse gas emission, so increase in oil price as well as depletion of fossil fuels, all motivate us to switch over from that fuel-based vehicle to the electric vehicle. So when you see the advantage of electric vehicle compared to the fuel-based vehicle, so it is energy efficient. 59 to 60% of the electrical energy from that battery can be used for the running of the vehicle, whereas only 70 to 21% of energy from the fuel used for that car functioning and all. So that energy, if you see that high energy, that it is energy efficient. Electric vehicle is energy efficient compared to fuel-based vehicle, and it is environment friendly. There is no CO2 emission when you are using that electric vehicle, and it is very smooth to operate. There is no noise, nothing. And then it reduces the energy dependence. Electricity is domestic energy sources. Wherever you go, simply you can connect and then charge your the battery in the car. While talking about the advantage, there are several challenges are there when you use that electric vehicle. If you see the driving range, so EV, electric vehicle, it can go about 300 kilometers. Whatever the electric car available at India, it can go about 150 to 200 kilometers right now. And then Tesla only, they have introduced that EV which can go up to 450 kilometers. So the driving range is less compared to that the fuel-based vehicle, where in a single, so once you refill, you can go about 450 kilometers when you use petrol or diesel. In that case, it is less compared to that fuel-based vehicle. And then the more important thing is recharging time. So it will take nearly 5 to 8 hours when you are charging. So where the chemistry comes into the role, if you have that developed material which can, as I said earlier, if you have that the material which can use that during the charging and discharging, there is a fast diffusion of ion, then you can increase the discharging time. So there, the chemist, they will play important role to education. And then the battery cost. Battery packs are very expensive. if you see that, so where we have to, how we can minimize that the battery cost. That is important. That's what the available electric vehicle in India, it is expensive because we are importing the battery from the foreign countries, particularly from China, Korea, and then US, Germany. From that we are, when you are importing that battery, so all the cost it will add up. So the custom duty, there are many taxes involved in that, and then whoever the dealer, they have their own benefit. All it will add up, and then ultimately your the electric vehicle is very expensive. So if you have that indigenous battery, so some company, they are fabricating that battery in India, then you can bring down the cost. That's where the indigenous development is very important. Then that weight and volume, if you can see that the weight, it is nearly 500 kg to 1 ton, it will be there. So that, so again there you have to play with the material chemistry to bring down that weight and volume. These are all the challenges it is there in that electric vehicles. This slide shows that the electric car which was introduced by that various automobile companies, starting from that Nissan Leaf, Mitsubishi, Tesla, and many Japanese companies, they are involved in that the electric vehicles business. If you can see that among these all that the electric vehicle which was introduced by Tesla, which is having the capacity of 85 kilowatt hour, which can go up to 425 kilometer. Now, recently you might have read that the million mile battery and all, that the Chinese based company and all, they are introducing that million mile battery. Even Korea also, they are introducing that million mile battery. It means, so you can travel, so you can travel up to 1 lakh kilometers. 1 lakh kilometers, and then if you can calculate, so normal battery, it will come about nearly 5 years, considering that 1500 charge discharge cycle, it will come about the 5 years. If you calculate that the million mile battery and all, it will come more or less close to this. But the very attractive word is million mile battery. So here the Tesla, this is the highest capacity. The capacity is directly proportional to the driving range. When it comes to that the local Indian market, only that Mahindra, they have introduced the two car. One is E2O plus, one is E-Verito, which can go about 140 kilometers. 16 kilowatt hour battery, it can go 140, and another one, it can go about 110 kilometers. So in addition to that, the battery pack also used in the hybrid cars, where very low capacity of the battery used in the where they are integrating with the fuel-based vehicle for start-stop application. So in addition to that, there are various companies who are all working on the two-wheeler. So two-wheeler and three-wheelers. For example, Ather Energy, they are working on so lithium-ion battery-based the two-wheeler bikes. And then in buses, Ashok Leyland, they are working on the lithium-ion battery-powered e-buses. So it is not come to the commercial market, still under testing. So considering that the importance of this electric vehicle, the government of India, they have made that National Electric Mobility Mission. So in 2011, so to switch over from that, to speed up the transition of fuel-based vehicle to the electric vehicle, this commission was established in 2011. As per this commission, so this commission aimed to deploy nearly 6 to 7 million electric vehicles on the Indian road by 2020. Already we are in 2020. It is kind of ambitious plan, but still that commission is trying to push that the electric vehicle on that the Indian road. So what is the requirement? Considering that 200 kilometer range UV with a 50 kilowatt hour battery pack, it would take approximately 0.7 million tons of the NMC and then 0.35 million tons of that graphite to meet that this 6 to 7 million electric vehicle. If you want to so fabricate the battery for this 6 to 7 million electric vehicle, this is the material requirement. It is in the million tons of cathode and then million tons of anode is required to meet the requirement. And then also this the electric mobility mission, they are giving the subsidy through that FAME, which is called Fast Adoption and Manufacturing of Electric Vehicle. So next slide, I will show you that for four-wheeler, two-wheeler, how much subsidy we are getting when we are using the EVs. So the important thing I want to highlight here, so once we are achieve this target, for example, 6 to 7 million electric vehicle, so we can save up to nearly $300 billion, which we are spending, nearly 20 lakh crore, which we are spending for oil import. And we can avoid the release of 1 gigaton of CO2, which we are emitting through the various things that we can so avoid. This is the advantage of implementing that EV technology, particularly for the vehicle sector. Hold on, this is not moving. Yeah, okay, yeah. Sorry for the disturbance. So, these slides give you that a clear picture when you compare that fuel-based vehicle with the electric vehicle. So this Phobos India, they have given that very interesting statistics. Considering the average person drives 10,000 kilometers per year. When you are buying that the electric vehicle, the cost is about 8 lakhs. In that, battery cost is about 3 lakhs, which is nearly half of the cost of the vehicle. And when you are charging, so you are spending nearly 50 rupees per charge, and then you can drive about 100 kilometers per charge. Considering that the 10,000 kilometers per year, you are spending only 5,000 rupees per year. Whereas when you are purchasing that fuel-based vehicles, the cost is 5 lakhs, and then your mileage, considering the mileage of 10 kilometers per liter within the city, and then considering that the petrol price of 75 rupees per liter, for driving 10,000 kilometers per year, you have to spend nearly 75,000 rupees per year when you are using the fuel-based vehicle. For battery vehicle, the running cost is only 5,000, whereas a fuel-based vehicle, the running cost is 75,000 rupees. It is nearly 70,000 rupees more than that of the electric vehicle running cost. So the other important advantage here is there is no CO2 emission into the atmosphere, and then you can so avoid that importing of oil. Nowadays, that oil price keep increasing, and then we are spending huge amount for oil import. So by doing this, definitely we can so avoid all these expenditures which we are spending huge money for importing oil from the Gulf countries. So another thing I want to highlight here, the cost, if you see electric vehicle cost, it is 8 lakhs. So the battery cost is nearly 3 lakhs. As I already mentioned, most of the battery we are importing from that abroad. That is the reason the cost is expensive. If we have our own technology, then we can bring down the cost of that battery, and which will reflect in the overall cost of that electric vehicle. That's what we are trying to do in RCA. So recently the government announced subsidy under FAME 2. So when you are using that two-wheeler, so you will be getting that the subsidy nearly about the 20,000 rupees per kilowatt. You will be getting that 10,000 rupees, and then 2 kilowatt hour battery you will get 20,000. When you are using three-wheeler, you will be getting about 50,000 subsidy, and for car you will be getting 1,50,000. And then that four-wheeler for a hybrid vehicle and e-bus and all. So the subsidy is huge. By giving this subsidy, government is trying to push this electric vehicle so that we can get rid of all this oil import and then that global warming and all. And then recently, the government announced when you are buying that two-wheeler or three-wheeler, which is based on that the battery-based the two-wheelers, three-wheelers. you don't need to buy that battery. Only you can buy that bike or rickshaw, and then that battery it will be owned by that company. So like whatever we are refilling that gas for the cooking, right? So that way you don't need to spend that money for the battery, because battery is coming half of the cost of any two-wheeler, three-wheeler or four-wheeler. Now the government introduced for a two-wheeler and three-wheeler, you don't need to buy the battery, only you buy that the bike. So that the cost, it will match the cost of that fuel-based vehicle, so that the customer it will be getting benefited, and it is attractive to the customer to buy that more EV based vehicles. So another big market of lithium ion battery it is mobile phone. So everyone having that the mobile phone in India, and a huge requirement is there for lithium ion battery which can be used in the mobile phone. But the unfortunate is no single company in India making that lithium ion battery which is used for that mobile phone. It is very small capacity lithium ion battery. We don't have single company in India. That is very unfortunate situation in India. So we are importing, but so we are not interested to develop the technology. So this slide shows that why we need that indigenous lithium ion battery material technology. So this pie chart shows that various components involved in that lithium ion batteries. So the numbers are these numbers contributing to the overall cost of the battery. For example, if you see 32%, the cathode material which used in the battery contributing nearly 32% of the cost, and then that separator contributing 80 to 18%, and then electrolyte 15, and then anode 11%. Overall, if you see cathode and the anode material, nearly 40 to 50% of cost, it is coming from only material. So if you have the developed material which is cost effective, that really it will bring down the cost according to these statistics, because 50% is cost is material in the battery. That's where ARCA trying to develop that indigenous material technology. So by the cost effective and the large scale process to produce the cathode and the anode material in large quantity, so that this material can be supplied to the company, they can fabricate the battery for various applications. And ARCI, so we have taken that two important energy related project. One is the development of lithium ion battery for EV application, which is cost about 20 crores. So in way of 2011, we started this project where we set up that the pilot plant facility for the fabrication of battery, and also we have developed the indigenous lithium ion battery material by large scale process. So the another major project which is ongoing is the Technical Research Center for Alternative Energy Material and System. So there are so the government of India, they have selected 5 institutes to set up that Technical Research Center. ARC is one of the center. So we mainly focus on that energy related thing, and we are working on various energy related topics like lithium ion battery, supercapacitor, solar cell, and then fuel cell. Our group, we are working on the material development for supercapacitor application. So the main objective of ARC is, one is we want to set up the pilot plant facility for the development of lithium ion battery. So we have invested huge money buying that various equipment which can produce the battery starting from the powder to battery. So we have established the material, and we have established that the protocol, the know-how procedure, how to fabricate that battery by optimizing that various the process. The other objective of ARC is development of indigenous material. So we have been working on that various cathode material and the anode material. Today I'll be presenting the activities related to lithium iron phosphate and then lithium titanate. So now we have established the procedure to continuously produce this material in large scale, and this material we are giving to our pilot plant facility. So they will be making that battery with our own indigenous material. These are all the two important objectives of ARCI, that battery technology initiation. So this slide shows that the facility which we have been established at ARCI Chennai. So for the complete fabrication of the battery. So we will start with that the powder where it mixed with that the binder and additive, and then later we do that coating on the current collector, and then we do that densification by the calendering, and then according to our the length of the battery or width of the battery, we do the slitting of that the electrode, finally do that winding, and then for the terminal we do that the welding. So finally, when we do that electrolyte filling, after this is the cell we have fabricated at ARCA. And this is since the electrolyte and the other electrode material which are very sensitive to that moisture and oxygen, we are doing all this process at dry room condition. So the 30% relative humidity maintained for that coating machine, and then 0.5% RH it is maintained for the fabrication of that cells. These are all the different cells with a different capacity. So we have fabricated at our facility. So 12 volt 10 ampere hour, and maximum we have done that 48 volt 10 ampere hour lithium ion battery cell. So for this lithium ion battery plant, you need that huge amount of that material for process optimization. And if you want to prepare the 100 cells and all, again that the amount of material required is huge. Initially, what we have done, we don't have material. We have continuously so imported from that foreign country. After some time, the company asked why you are importing such a large quantity of material, and then they stopped that the supply. When we are keep demanding, then they have increased the price. So when we are keep depending on that the foreign company, this is the issues. And then realizing these issues, ARCA has taken up that the material developmental activities. We try to develop our own material which is used for electric vehicle application. So these are all that the commercial lithium-ion battery having that the different kind of the anode and then battery, different battery chemistry involved in that lithium-ion battery. For example, the NCA-based cathode chemistry used by that Tesla and all, they are using Panasonic, Benz, they are using this NCA-based battery chemistry, and then manganese-based LG Chem, lithium iron phosphate. Lithium iron phosphate, the voltage is 3.2 volt, whereas NCA is 3.6. Even though the voltage is less, so it is extensively used in the China. Last year we went to China for some so inspection of our equipment which we purchased from the China, and then you can see that the road, all are electric buses which is running using that the iron-based lithium-ion battery. So the main advantage of lithium iron phosphate, it is very cheap compared to the other the cathode material like NCA and then NMC. This is mainly used by that this NMC also mainly used in many Japanese company, they are using in their battery. And then the other the battery chemistry which is really interesting is lithium titanate. This is the anode material, and then the advantage here lithium titanate, it is extensively wide the temperature, operational temperature range. For example, it can go up to 60 degree also the battery is stable. Even if you can go up to minus 30 also, the battery is very stable. Whereas NCA and NMC and all thermal stability is very poor. So country like India, we need that the cost effective material as well as the battery material which is stable for the wide temperature range. For example, even summer and all, our temperature it will go up to 50 degrees centigrade. So the selection of material according to that the temperature and considering the cost, it is very important. So considering the cost aspect as well as temperature, we have selected these two battery chemistry. And so the other important thing is the Mahindra battery, who are all interested in this battery chemistry. LiFePO4 as a cathode, graphite as a anode. So they are interested in this, and then we have taken up and we developed that the technology for large scale production of LiFePO4. And then the Toyota Suzuki Corporation, they are very much interested in lithium titanate, considering the climatic condition in India. So because the Toyota Suzuki Corporation is Japanese-based company, they have well-established LTO technology in Japan. They are looking for LTO technology in India. So they are visiting many institutes and the university who are all working on LTO. And then when we came to ARCA, they are very much impressed with our technology. And I will show that the highlights of the LTO technology which is developed at ARCA. And this is the material processing, how we are doing the material processing, and then how we are characterizing that prepared material, and how we do the benchmark with the commercial material. So unlike that wet chemical method, we are using the solid state method for synthesizing that the cathode and the anode material. When we are using the wet chemical method, there are a lot of solvent involved in that. And then handling issue as well as these solvents are very expensive. So we want to develop that solid state method. And then there are laboratories, lab scale planetary ball milling available as well as high energy milling unit. Why we have chosen this high energy milling unit is there are a lot of advantage. It is short process time compared to the lab scale planetary milling. It will take nearly 24 hours. With this, we can do within 2 hours. We can do that whatever the requirement. And then because since you are running milling for short time, your contamination is less. So why this short processing time is whatever the energy input which we are giving is very high due to high relative velocity of balls. Because that high energy input that we are giving, that is the reason short process time. When you are running a short time, your contamination due to stainless steel and all, it will be less. And then the other important advantage here is production rate is 2.5 kg per batch you can operate. So once we synthesize this material, we do that after milling, we do that heating. Finally, this material we extensively characterize for structural, morphological, and other elemental thing. We do all that characterization, and then we fabricate that electrode using this material. For example, 80% of active material, that is LiFePO4 or LTO, we take 10% of carbon black, 10% of binder. Binder, it will help for the addition of this material on the current collector. So with this, we will make the slurry and then coat on that either aluminum foil or copper foil. We make the electrode and then we do the testing in half cell or full cell mode. Similarly, for that coin cell also, we used to fabricate and then do the testing. So I'll also be talking about the development of porous carbon material for supercapacitor application. More or less, that the electrode processing, everything is same for both lithium-ion battery and the supercapacitor. And then, so there are a lot of the equation involved in that to estimate that the material performance. First, I'll be talking about the lithium iron phosphate. So as I mentioned earlier, so there are a lot of advantage when you are using lithium iron phosphate. It is very safe and secure technology. As I mentioned, there is no thermal runaway. Thermally, it is highly stable, very low toxicity for environment. When we are using other cobalt-based one, it is highly toxic. Here, it is a cobalt-free cathode material, and then the calendar life it will come 10 years, and the long cycle life. If you see the electrochemical characteristics, the capacity of this LiFePO4 is nearly 170 milliampere hour per gram, and then the voltage is about 3.4 volt versus lithium. But the limitation, if you see that it is kind of semiconductor. Because of that semiconducting property, the low electronic conductivity and the ionic conductivity. As I mentioned during that the charging and discharging mechanism, when your material having the good electronic and then ionic conductivity, the mobility of ions and then electron, it will be faster. For that, this is the limitation because it is having low electronic and ionic conductivity. What we have done, so we have synthesized the carbon coating on LiFePO4, kind of in situ carbon coated LiFePO4. We have synthesized through that solid state process. So we have taken lithium carbonate precursor, lithium carbonate as a lithium precursor, and then ammonium dihydrogen orthophosphate as a phosphorus precursor, and then iron oxalate as a iron precursor. All three precursor we have milled at a high energy milling, and then after that milling we have made that kind of the compact. So just we have pelletized by applying load, and then these pellets are loaded into that pit furnace. When we are heating at that 650 degree centigrade, lithium iron phosphate it is forming. By releasing the other byproduct is CO2, ammonia, and then all this it will come out. Finally, you will end up with that nano-size particle, nano-size LiFePO4 particle. So what we have done is we have synthesized the material and we have characterized site. And then if you can see that XRD, it is showing the pure phase of LiFePO4. And then if you see that the particle size, it is in the nano size. And then when we do that, the electrochemical performance, always we use the commercial material. We buy the commercial material. Under the same condition, we prepare electrode. And then we prepare the cell and then see that where our material performance in comparison with the commercial material. For example, so if you see that we have tested in that half cell mode where lithium used as a anode material and LiFePO4 with the carbon coated used as a cathode material. This is the typical charge discharge profile of lithium ion battery. When you plot specific capacity versus potential, if you see that the ARCA material, it can store energy about 140 milliampere hour per gram. Whereas the material from that Toda, the Japanese company, it can store about 143 milliampere per gram. If you see the energy storage, the material which we developed at ARCA is on par with the performance of the material performance of Toda. And then our material performance is better than that the LiFePO4 which is supplied by that UNTPL company. And then if you see that cyclic stability, so whatever the energy stored at the first cycle, it is 141 milliampere hour per gram. And then even after 200 cycle also, now so we have 1000 cycle data also, hardly 1 to 5% capacity decay is there when you are increasing the cycle. So that's where that the material is showing that capacity which is on par with the commercial, and also it shows long cyclic stability. It is not moving. No. Wait.
Devendra sir.
Yeah. 1 minute. No. Yeah. So we have developed the material where that the performance is on par with the commercial material. Then we have done that upscaling. How to do that upscaling? We have optimized that experimental parameter to produce 2.5 kg per batch with the performance whatever we are getting in that large scale level. Then after this the upscaling, so we have used this material for that lithium-ion battery fabrication using our indigenous battery facility, and then this is the battery we have fabricated with our material. The specification of our battery is 3.2 volt, 2.5 ampere hour battery we have prepared, and then with these are all that battery which is prepared our material, and then we have demonstrated. The major achievement here is prototype LiP device has been successfully fabricated and demonstrated using upscaled LFP. And then now we are fabricating the battery which is required for that car. So we have done that, and then only that demonstration is so pending now. So when we are working on this, the LiFePO4, and then that the Defense Institute called NSTL, which is located at Vizag, they approached us for that LiFePO4 supply. Why they have approached initially? What happened is they have imported material from China, and then they used that material, and finally the material is not working for their target application. For they are using the material, the battery for torpedo application, where you need that high power delivery. The battery, it has to deliver that high power. So whatever the material they are getting from China, that is not giving that performance what they expected. Then we have supplied whatever the material which we have synthesized, and then these two graphs you can clearly understand how the ARC material is better than that commercial material which is purchased from China. If you can see that we used to call that a different C rate. 1C current rate means charging it will take 1 hour. 2C means it will take only 30 minutes, half an hour. All C by 10 and all it will take 10 hours. So the battery which is fabricated from the China, it is working only for lower current charging. Whereas even fast charging within 30 minutes, also the ARC material is able to deliver the power. That's what, we develop the material according to the target applications. So the many companies, they are interested in ARC technology. For example, HPL Power System, Leaf V Drive, they are looking for e-rickshaw application. And then that ITI Bangalore, they are looking for a LiFePO4 battery for solar street application, and then modem, and then Alax Minerals Limited. So the other material, so which I'm going to present is a lithium titanate as anode material, which we have developed. As I told you earlier, so it can operate in the wide temperature range. Minus 32 plus 65 degree it can operate. The other advantage is zero stain material. So usually they are using graphite as a anode material, because a lot of the solid electrolyte interface formation happens that deteriorate the performance of the battery. So lithium titanate is an alternative to the graphite anode material. Like LiFePO4, this also suffer with low electronic and then ionic conductivity. What we have done, the same solid state process we have used, and then kind of to address this ionic and then electronic conductivity, we have prepared nano size LTO particle with carbon coated one. So we have optimized the procedure to produce 2 kg per batch, the LTO. And then when we see that the performance, like LFP, we have compared with the commercially available LTO materials, ARC material, it can store nearly 169 milliampere hour per gram, whereas commercial, it can store only 116 milliampere hour per gram. So huge difference in terms of performance. Our material shows high performance. And then this material we have used in the pilot plant, and we fabricated the prototype. And then considering that the uniqueness in terms of synthesis and then material property and then performance, we have filed this LTO technology in Indian patent we filed, as well as the 5 foreign patent also we filed for this LTO technology. The major achievement is developed a cost-effective LTO process, and we have demonstrated in the device level. So the highlight is, one is we can able to synthesize that nearly 150 nanometer size particle with the 80% particle size. Uniform distribution is nearly 80%. And then, so the scientist or the professor who are working in that milling area, they know that. So in order to avoid the stacking of material during that milling, we usually use that process control agent. That process control agent, what we have done is, after milling, that process control agent, it is converted into carbon material. So under atmospheric heating, so that finally we end up with the carbon coated LTO. So the advantage, the highlight is here, whatever the process control, it is acting as a dual role. The stearic acid has a dual role. One is process control agent, another one is, it is creating some carbon coating on LTO with this uniqueness, small particle size, and then carbon coating. We address that the low electronic and then ionic conductivity. So we develop the process and then how to indigenize the LTO material technology. So the two precursors we are using, one is lithium, another one is titanium. Titanium dioxide we are used as a titanium precursor. As you know, titanium dioxide available plenty in India. So we don't need to import titanium dioxide, but lithium precursor we are importing from abroad. And then, so BRC, the Mumbai, that institute, they have approached the ARCI. They are getting lithium carbonate as a byproduct in one of their process. We got that lithium carbonate from them, and then we have synthesized that LTO using their lithium carbonate. And we have compared that the LTO, which is synthesized using imported lithium precursor. If you see that the LTO using BRC precursor as well as the imported precursor, both are giving the same structure. The purity wise same, there is no compromise in that property. And if you see the performance, the LTO, which is synthesized from the BRC and SRL precursor and Toyota, all are giving the same. And then another thing, if you see that the rate capability, whenever you need that high power, the LTO, it can deliver that high power. For example, I will tell you that 1C means 1 hour charging. 10C, it means only 6 minutes it can charge and then discharge. Even at the 10C, the material able to deliver nearly 120 milliampere hour per gram. And then even 30C means nearly, so only 2 minutes per charging discharging. That also, it is very attractive for this LTO technology for high power application. The important thing I want to highlight here, the LTO synthesized from all precursor, it is giving the same performance. But if you see the cost of the commercial grade Li is CO3 is 11,400, whereas the Li to CO3 supplied by BRC it is only about 1,500. So indigenous precursor is 1,500, imported one is 11,000. And then by using this low cost precursor, you can bring down the cost of LTO nearly 2,500 rupees. Now the cost of our LTO is less than 2,000 rupees. So it is not only about that large scale, but also we have to prepare that large scale battery called pouch cell or cylindrical prismatic cell. We have tested in that pouch cell level, and then if you can see the performance, 80% retention you can get after 1,000 cycles. So that is the advantage, not only large scale, even at large battery pack also our material able to deliver that high capacity for long cycles. So far I talked about that the lithium-ion battery material developmental activities like LiFePO4 and then so lithium titanate anode. So the many companies they are interested, we are in discussion with them, and then the third-party evaluation also important. We are checking and we are giving the performance. When the third-party company like the Japanese company or other institute like VSSC, if they test and then give the certificate, then it is easy for us to convince that the company. That's what now we are doing the third-party evaluation, and then once it is done, we will transfer the technology to the industries. So the last topic which I'm presenting is supercapacitor. So unlike battery here, supercapacitor, both electrodes are only carbon-based electrode. There is low lithium involved in that. So like fossil fuel, lithium ion also it is available only limited sources are available. Once lithium is fed up, then you have to go for alternative energy storage. That is the reason people also working on that supercapacitor, which is carbon-based electrode. So that in the lithium-ion battery, the charging, discharging happening because of that oxidation redox reaction. Here, it is only that the electrolyte ion getting absorbed, desorbed on that electrode surface. So very simple example, I will tell you that. So what is the difference between the lithium-ion battery and the supercapacitor? Supercapacitor, it can charge within a minute, but it can deliver energy only for short interval. Like 100 meter dash, all athletes, they will run with very high power, they can run very fast, only for short distance. So it is like a supercapacitor. They can so instantly deliver the power within short time. When you see that lithium-ion battery, so you need that high energy, but it slowly so deliver the energy. For a 10-kilometer athlete and all, they should have that energy at the same time. They have to run very slowly, unlike that 100-meter dash. So this is the difference between that lithium-ion battery and the supercapacitor. In between this lithium-ion battery and the supercapacitor, there is called hybrid supercapacitor, where kind of a 800 meters or 1000-meter race, you have to run fast. You should have energy as well as power to win that the 1000-meter race. So here, if you see this graph, this graph is that rechargeable battery. Your voltage is stable. That's why it gives that long time. But if you see that supercapacitor voltage profile, there is a linear drop, but it can deliver that power very high, and then it sustained for very short time. So what is the motivation? What we can work on that supercapacitor? So like lithium-ion battery material, here also nearly 40% of total supercapacitor cost is for material. So we focused on that the material synthesis from that various bio waste. And then when you want to commercialize any material, you have to consider these three aspects. One is performance, cost, and the durability. So in the commercially, Maxwell, they are selling that supercapacitor. They are using the coconut shell derived carbon in their supercapacitor. So you can ask that there are plenty of coconut shell available in India. Why don't we use those carbon from coconut shell? So this one Kurare company who is making carbon from coconut shell, they observed that the coconut shell from India, it is not suitable for supercapacitor grade carbon because our coconut shell having lot of minerals. So when you are heating at high temperature, it is converted into oxides that gives the more resistant during the electrochemical reaction. They found that coconut shell from Philippines, it is the ideal coconut shell which is having less ash content, suitable for that supercapacitor grade carbon. So ARC, what we focused on using of cost-effective carbon source like jute stick, pet coke, and then waste cotton used as a carbon store to produce the carbon material. So this is the jute plant which is available plenty in the coastal Andhra. Very interesting statistic is, so this jute fiber, it is having the commercial value, but the jute stick, doesn't have any, it is used for that domestic purpose for cooking or benzing and all they are using. So we have taken this jute stick as a carbon source because if you see that the availability, extracting every tons of jute fiber, you will be end up with 2.5 tons of jute stick, and per annum 4 million tons of jute stick dumped as a solid waste per annum. So that is the reason we have taken as jute stick as a carbon source. So we have used that KOH based chemical activation, and then more importantly, so we have converted this jute stick into graphene-like structured carbon, which is confirmed by that the Raman spectroscopy as well as the TEM and SEM shows that graphene-like structured carbon formation, which was confirmed through this electrochemical characterization. And then like battery, we have tested this the porous carbon material for supercapacitor application and compared with the commercial material. If you see the performance of ARC material, it is giving 132 farad per gram, whereas commercial material, it is giving only 91 farad per gram. And then if you can see that the 10,000 cycle, that the material is stable with the less the decay in the capacitance. So this the entire process we have filed Indian patent, and as well as we have published some good papers out of that. But still the challenge is when you are taking that when you are using jute stick as a carbon source, final yield only 35%. What we have done, we have used another kind of waste called the petroleum, petcoke. 1 minute, so it's not moving. Wait a minute, it is not moving. Sorry. Another 10 minutes, I will finish my talk.
Okay, sir, no problem.
Suddenly it is not moving. I'll try to do that. Yeah. So the previous jute stick, the problem is that yield. Yield we are getting that only 35%. So then, so we have identified that the petroleum coke, which is one of the byproduct during the petroleum refining process. This HPCL, the Bangalore, that they have approached us, and then they have that plenty of million tons of pet coke they are generating as the waste. They approached us whether we can convert this pet coke into carbon material, which can be used in the energy storage device. By develop that the process technology, we convert this petroleum coke into the porous carbon material. So unlike juice stick, here we are getting the yield of 60 to 70% because the raw material itself it is having 90% of carbon material. So we converted into porous carbon material, and then finally, like jute stick, we could able to get that graphene-like structured carbon. And then if you can see the performance, this is the commercial the carbon porous carbon, which is giving about 98 farad per gram, whereas our indigenous carbon, which is synthesized from the pet coke, it is giving 128 farad per gram. And when you dope, it is further increased about 159 farad per gram. So the high performance, low cost. So this is available. So the petcoke, the cost is $100 per ton, very cheap. And then we use this the petcoke as a carbon source, and then yield is very high, and then performance is better than the commercial carbon, which is used in the Maxwell supercapacitor device. And then recently we filed this process also as one Indian patent. So for this material, once we establish a lab scale process, now we have done that all that upscaling activities. So there are so many parameters we have optimized, starting from the activation agent, concentration of activation agent, activation temperature, holding time, and the rate of in so many parameters we have optimized. Now we could be able to synthesize 220 gram per batch. So, and then that performance also, it is whatever the upscaled performance, also it is comparable with the carbon which is synthesized at the lab scale level. This kind of the electrode we have prepared. So that I will cover in that later. So I was telling about that we could be able to synthesize the graphene-like structured carbon. So what happens? So we are doing that as it is any bio waste. If you are heating at inert atmosphere, it will give that the carbon. Any bio waste if you take, but the tuning the pore size, getting that high surface area. So the tuning that the textural parameter is important. There are certain requirement for that supercapacitor grade carbon. You have to meet that requirement. So one of the requirement is if you prepare the graphene-like structure carbon, you will get that high electrical conductivity. What happens when you mix that we are using that KOH based chemical activation. So we are mixing this KOH with the bio waste, and then through all the electrochemical redox reaction, it forms the potassium carbonate. And then what happens to this potassium? This is the one that initial precursor where that the graphite microcrystals bonded with that sp3 carbon. So this potassium ion first break that the sp3 bond, and then so you can see that here. So when you go at high temperature, this the potassium ion, the graphitization, catalytic assisted graphitization, it will be there. So it increase the graphitization, and then you will end up with a kind of good graphene-like structured carbon. And then when you go for at high temperature, all this microcrystal it stack together, and then there are kind of due to that van der Waals forces, it forms that the graphene like few layers of graphene like structured carbon. So this is where this our technology is valuable to synthesize the graphene like structured carbon from that various waste. This is the summary of the various waste which we have used as a carbon source to convert into porous carbon material through chemical activation as well as physical activation. If you can see that the petroleum coke yield is very high, as well as the activated carbon, coconut-based charcoal, which is also it is giving that 60%, but performance-wise, this is giving the better performance. So overall, we have developed a cost-effective process to synthesize the porous carbon from the bio as well as the industrial waste and fabricated the indigenous device. The company which are interested in our ARCA technology for making porous carbon is HPCL, SPEL, and then EcoGreen Cleantech Limited. So another thing what we have done is we are planning to fabricate the supercapacitor device and for a demonstration of electric vehicle application. What we have done is commercial supercapacitor we purchased and then assembled in a model, and then with that supercapacitor model we demonstrated for bicycle. This is kind of proof of concept. Our actual application is different, where we are using the supercapacitor for cranking applications. So proof of concept, we demonstrated for the first time using supercapacitor model, we can drive the bicycle. So our ultimate aim is we want to prepare our own supercapacitor device. For that, we have established that the semi-pilot plant facility for the fabrication of supercapacitor device, starting from the carbon material to the final device. These are all the equipment we have purchased, and then recently we have set up the facility to fabricate the supercapacitor device. And into this facility, we have coated this carbon which is obtained from the pet coke. It is coated on the carbon electrode. So this is the carbon electrode roll. Later, kind of cathode, anode, the white color is separator. This we have made a kind of 50 mm diameter jelly roll. This is simply, it is kind of electrode we binded by keeping the separator inside. Later, this it will go inside the aluminum can. After electrolyte filling, we will get this kind of the device. The target device voltage is 2.7 volt and then 1000 farad. These are all the various process involved in that. So after coating, we have winded this electrode, and then we have to take the terminal in the bottom as well as in the top. So what we have done, whatever the uncoated aluminum foil, we have flattened in the top and the bottom, and then by welding this guide plate on the bottom and the top, we have taken the positive and the negative terminal. Finally, this one, it goes into the aluminum can, and then after sealing through this coal electrolyte we will fill, and then finally you can see this is our own indigenous supercapacitor device using ARCA porous carbon material. Recently we have completed, and the performance, if you can see that compared with the Maxwell supercapacitor device, almost it is giving that the same performance now. So this is the last slide of my thing. So that I so far talked about lithium-ion battery, which can store more energy but slowly it charges. I talked about supercapacitor, where it can charge fast, but it can go for only limited energy. Only it can store, because it involves here. If you can see that it is the physical phenomena, only absorption desorption taking place during charge discharge, whereas in the lithium-ion battery, the electrochemical redox reaction taking place. That's why it can store more energy. What we have done, we combine together. One electrode, we put that battery electrode, another one is the capacitor, supercapacitor electrode, and then trying to increase the energy of the supercapacitor, because the energy density here it is only 10 watt-hour per kg. Here it is 250 watt-hour per kg lithium-ion battery. So by doing this, you can improve about 25 watt-hour per kg. That is our the intention. These are all the advantage of lithium-ion based capacitor. And then this one shows that where the lithium-ion capacitor performance. If you can see that this one, the green one, supercapacitor. So the energy density is very low. And then if you see the power density, it is very high. It can deliver instantly the power. And then the blue one, if you can see that, it is having the high energy density, but the energy density is very poor. Sorry. The red one is battery. It is having the high energy density. If you see the x-axis, very poor density, poor power density. Whereas the supercapacitor, high power density, and it is having very low energy density. So to get that device which is having the high power density as well as high energy density, this is the material we have so developed, which is showing that the energy density, power density in between the lithium ion battery and the supercapacitor. So that is the thing. And then we have demonstrated this one. So these are all that you can see that clear difference. So when it is supercapacitors, if you want to store that the energy, you need that 340 kg. The same one lithium ion capacitor, if you have that one cathode lithium ion battery, one electrode, supercapacitor based electrode, you can bring down the size of the device drastically, because the lithium ion battery electrode, it can store energy, whereas supercapacitor electrode, it can store less energy. That's why it will occupy the huge volume, whereas lithium ion capacitor occupy only less volume. This is the summary of my talk. So lithium ion battery technology is very essential to reduce the CO2 emission and then global warming. So large scale synthesis of cathode and then anode material by pilot plant facility has been successfully established at ARCA, and then performance is on par with the commercial one. And so as I mentioned that porous carbon material also we have developed. Not only that material, also we set up the facility for the fabrication of device. So that also it is showing good performance that we are trying to use for some other application. So all the benchmark studies reveal that the performance of material which is developed for lithium ion battery supercapacitor, it on par with the commercial material. Finally, I would like to acknowledge our management. I thank my director, Dr. Badmanabhan, for giving all support, all kind of facility for carry out all these energy related projects. And I thank Dr. T.N. Rao, he is my immediate boss. So he only initiated the lithium ion battery activities at ARCA. And I also thank Dr. Kopalan, who is Associate Director, now Regional Director at the ARCA Chennai Center. And I also thank my former director, Dr. Sundararajan, who initially established all these facilities and then got that all the major projects related to that lithium ion battery and then supercapacitor. I would like to thank all my colleagues and then my team leader, Dr. Vijay, and the other colleagues for their support. And then finally, my special thank to my students and the other project staff. Without their help, we would not complete all this the achievement. So finally, I would like to give small information. If students are there, they'll be getting benefited. So ARCA, now we are giving the opportunities for, so it is there for a long time. Just for your information, I'm telling, for a student who are all doing that final year in BSc or not BSc, MTech, BTech, and then MSc student, they can do the project work at ARCA starting from 3 months to 1 year. Just they have to send their CV to the HR, and then they will circulate among the scientists who are interested. They will take that, recruit that student, and then they are ready to work in that ongoing that projects. And then in addition to that, we are giving that whoever graduated MSc, BTech or MTech student, we are giving 1 month, 1 year training program with stipend. So that also they'll be benefited. So MSc student and then MTech student. And then we used to give yearly twice, we used to give advertisement for JRF and SRF students. And then whoever qualified that clear that written exam and then clear that interview, they'll be selected for PhD. They'll be registering PhD in that NITs or IITs, and most of their research work they'll be doing at ARCA. Nearly 5 years ARCA is giving stipend for that all that research students. And for major projects, for example, I told you the TRC project, which is for the 5 years, we also recruit the project scientists for the period of 3 years to the 5 years. And then who are eligible, they can also apply. And then if they do the work later, they'll be considered for regularization also. These are all that the opportunities available at ARCA. Further detail, you can visit our website www.arca.res.in. And then interested candidate, they can send that their resume to hrd@arc.res.in. So finally, I would like to thank the organizing committee for inviting to deliver this lecture. And I thank all the participants for listening my talk nearly 1.5 hours. Thank you so much.
Thank you so much, sir, for your wonderful presentation. And from the organizers, I thank you, sir, for giving opportunity for the graduate students and postgraduate students. So our students are there, sir, in the participation. So I request Pravat Kumar and Maunika Tiwari. If you are really interested, you can contact. Sir has given the mail ID. So now I request Dr. Ashok, in charge for the questionnaire. Now we will take 3 to 4 questions. Dr. Ashok.
Sir, good evening, all of you, sir.
Good
Is it audible, sir?
Yes.
Thank you, sir. So thank you for the opportunity as a question in charge given by the organizing committee, sir. Sir, Srinivasan Anand garu. So we have a series of queries on your great talk, sir. So the first question raised by Venkatesh: what is lifetime for the battery if it can be used for 10,000 kilometers per year?
Yeah. So, for example, so per charge you can go that 140 kilo. For example, if you consider that 100 kilometer for one charge, if you can go that 100 kilometers. So, for example, usually that battery will come at 1,500 cycles.
Okay.
1,500 cycles. So, if you can add a 15, not 15,000. 1,500 cycle it will go, and then per charge you can go that 100 kilometers, right?
Yes,
so in that case you can go 1,50,000 kilometers.
Okay.
So it depends on what is the battery capacity in your car, how efficiently you are maintaining your battery. So instead of completely draining your battery, if you are always keep your, like our mobile phone battery, if you keep at 50% always, you will be efficiently using your battery. So if every time if you are completely draining means you are abusing the battery. So one thing is it depends on what is the battery chemistry involved in that. Based on that, so your driving range it will differ.
Okay, sir. Another question by Sai Sushma: what makes Tesla stand out amongst other manufacturers? What makes the price of the electric cars so exorbitant?
So the Tesla is the #1 company. So they have invested the huge amount for that electric vehicle. So Tesla car we cannot buy in India. So it will be very attractive. So as I mentioned in that presentation, they are using 85 kilowatt hour battery capacity in their car, which can go up to 450 kilometers. So will our normal middle class people will afford that 50 lakhs the car price electric vehicle? Who will buy in India?
Yes, sir. Yes, sir.
So it is suitable for that the US and all. Now the Tesla, what they are doing is they are tying up with the China-based company. So
Okay,
for developing that the cost-effective battery, so they have their all complete the battery fabrication process know-how they have. Now they are working on whatever the existing battery chemistry is. They are using nickel manganese cobalt oxide as a cathode, or nickel cobalt aluminum oxide as a cathode, and graphite as a anode, which having the higher energy density, and then you will end up with high driving range. But if you want to reduce the cost, you have to look for alternative material. That is the reason now they are looking for that lithium iron phosphate battery chemistry, where you don't have the cobalt, which is toxic as well as expensive. If you consider that LiFePO4 battery, so it is all the raw materials are cheap. So your battery it is cheaper, and then finally it will reflect in that your car price also. That is where now they are tying up with the Chinese company to establish the lithium-ion based battery.
Yeah, one of your slide mentioned, sir, outside abroad it was 8 lakhs and here it was 5 lakhs. So if you...
No. So that is, sorry, I think you have misunderstood. That is the cost comparison I have given.
Yeah, comparison only, sir. So if you not able, means if you import, you will get the pack.
Definitely. So
Yes, sir. Clear, sir. Thank you. Another question from Dr. Ashish Gandhi, sir. Considering huge requirement in the near future, what is the abundance of the material used for the batteries?
yes. So for lithium-ion battery, the heart of the material is the lithium source. So only in overall world, so usually they call that lithium triangle. Argentina, Bolivia, and then Chile. These three countries only they have that major lithium sources. So in addition to that, China also they are having the lithium source. So far, that all three countries they are supplying that lithium sources, and then all countries they are purchasing and then making the battery. If you are fed up with all these things, if you are no more lithium, you have to look for the other battery chemistry. Like now it is coming up sodium ion battery, and then potassium ion battery, and then this kind of the supercapacitor where you don't need any lithium. So it is only carbon based electrode. And then sodium ion battery, it will be very attractive because it is available plenty. Like lithium only, it is very limited sources available, whereas sodium it is available plenty. But there also advantage, the challenges are there because the energy density of sodium ion battery is less than the lithium ion battery.
Okay, sir. Another question, sir. What Srinath Reddy garu asking, what is the most important parameters to get the good efficiency of a battery?
So again, one is that as I told you during this one, yeah. So any that battery, most of the material, it is having that the low electronic and then ionic conductivity. When you are preparing that nano size particle, so your lithium ion diffusion kinetics, it will be faster. And then whatever the electron generated during the oxidation at the positive terminal, it should have the conductive medium to pass through the collector and go to the external circuit. So the nano size particle, which influence the ion diffusion kinetic as well as the good conductive medium kind of carbon coating on electrode material, it improves the performance. The another important thing is the battery chemistry plays an important role. Whatever the material which is having the high voltage, always you will get that high energy density that it will reflect in the long driving range.
Okay.
But again, there is a trade-off relation. If you go for the higher voltage, you have to compromise the thermal stability and all. You don't get that much long cycle life. You have to play with the battery chemistry according to your application. Depends on that the cost as well as the climate condition. For our India and all, so summer it will go up to 50-degree and all. So this NMC or NCA based battery chemistry, it will not be stable, and then it will come for instead of 1500 cycle, it will come for only 1000 cycle. Whereas the LiFePO for lithium titanate based material, it is a wide temperature range, and then the cost also it is less. That kind of the battery chemistry it is suitable. As I mentioned, this the size of the particle and then the conductive medium, the voltage, all it is placed in the role of the capacity of the battery.
Okay, sir. Another question from our student Pravat Kumar, sir. In the present, is the lithium-ion battery dominant in the electric vehicle industry?
Definitely, there is no question about that. So when that, as I mentioned, so the first lithium-ion battery it invented in 1976, and then it was commercialized in 1991. At that time, per kilowatt hour capacity, it is $1,000 it cost. Now many companies they started producing the lithium-ion battery. Now it has come $130 per kilowatt hour. So as long as there are many companies there for the production of lithium-ion battery, all the component cost, everything it is coming down. So now that lithium-ion battery, so at least for another 2 decades, you have to live with the lithium-ion battery.
Okay, sir. Another question from Navalika, sir. Can we use solar cells to charge these batteries, like even during using the vehicle?
Yeah, we can use, but again, it depends on that. It has to be continuously available, that solar light. So again, you need that solar panel. You have to invest in that, and then the DC current to that AC current, all that converter, everything it is required. So when you are adding more and more system, the cost it will be higher.
Okay.
So another important thing I will tell you that, so the one ITI Bangalore based company, they are using this battery for solar street application. What they are doing is this lithium iron phosphate based battery they are putting, and then they are assembling some the solar panel. During daytime, this battery getting charged from the solar, and then night it will be useful. But again, it depends on the application. That solar street light and all, it is no problem. But when you are using for that electric vehicle application and all, again it will add up the cost, and then how efficiently the performance. So if you are continuously moving, your whatever the light intensity also it varies, and then it will be peak. Whatever the solar light intensity, it will be peak only at in the middle hours, right?
Okay, sir.
No, it depends on that.
Okay, sir. Another question, sir, from CP Vardhini. What is the difference between lithium battery and graphene battery? What is the efficiency of graphene battery?
Yeah. So as I mentioned here, one lithium-ion battery where lithium-based electrodes are used. The graphene-based means carbon-based energy storage called supercapacitors. So here it can store energy. Lithium-ion battery supercapacitor, it can store only less energy because this chemical reaction involved in that in the lithium-ion battery, whereas in the supercapacitor only physical absorption desorption. Because of this physical phenomena, it can deliver the power instantly, but it cannot hold that much energy because the carbon material it cannot store that much energy like lithium-ion battery. But the advantage is here the supercapacitor. Wherever you need that high power for power backup, whenever there is a power shutdown, so you can use this one, but it will come nearly 1 million cycle lifetime. Because when you do that electrochemical reaction in the battery, there may be some degradation in the battery. But when the physical phenomena involved in the battery mechanism, there is not much change in the electrode. That is the reason it comes nearly 1 million cycle. It means 10 lakh cycle lifetime it will come. And then considering the advantage of supercapacitor, what they are doing, our lead acid battery. So people are using in that lead acid battery powered e-rickshaw in Varanasi. It is very popular. But the problem is it will come only for 500 cycles. And whenever there is a acceleration record, whenever there is a slope, this lead acid battery it unable to deliver the power. When you are integrating this supercapacitor into the lead acid battery, so whenever there is a high power record, the power it will run from supercapacitor, and then you are not abusing your lead acid battery. By integrating supercapacitor into lead acid battery, you are increasing the lifetime of your lead acid battery. So that kind of application, the supercapacitor, it is useful. Like lithium-ion battery alone, supercapacitor we cannot use it. For public transportation in abroad, what they are doing, supercapacitor bus, they are running within the city. Every 5 kilometers there is a charging station. So the bus it will get charged. It will run for 5 kilometers. By the time people get in, get out, it will get charged because it can store only energy to travel only 5 kilometers because the physical phenomena involved and only carbon electrodes are there for storing energy. So when you go for another 5 kilometers, so it will run completely discharged, and then because within 1 minute it can get charged.
Okay, sir. So, sir, shall I continue, sir? We have 5 to 8 questions are there in the chat box. Is time permits?
No, sir. Close it. It is already getting late.
So, one last question, sir. One last question, sir, from Haripadma Sri, madam. What is the yield of graphene obtained from pet coke? What is the optimum amount of lithium required for that? Sir, Srinivasan, sir. Hello?
Connection
I
problem
think,
maybe.
yeah, it was stuck actually.
Yes. Okay.
Sir, thank you,
Any
sir.
more? Okay.
Anyway, yeah.
Thank you, sir. Thank you very much. So if you have any doubts, then you can contact to Srinivasan Anandan sir. Sir already has mentioned his mail ID. So now,
He'll be back. He'll be back, sir. We'll wait. And
yeah,
before that, that announcement, should I before let
yeah,
sir join?
please.
Himabindu ma'am, are you ready, ma'am? That's okay.
Okay.
Right,
Yeah.
right. Let sir will come, madam. We have some announcement to be made. We'll make that. Vijay sir, do you have that list with you? You want to display?
Devendra sir.
Yes, already sent to you.
Devendra sir.
Devendra sir already sent to you. He said
Sir,
he
we
shared
can't-
with you. He shared with you. Yeah, from organizers, we have small announcements to all participants. Now we are sharing the participant list. Please check your name and institution details, mail ID, everything. You just kindly check so that the same will be posted onto your certificate. If you have any errors in the displayed list, please let us know by WhatsApp group or Telegram group or by email so that we can correct it. If you don't have any queries, please let it be as it is. We'll write the certificate name basing on these details. And even
Yes,
though
sir.
we are,
Is
yeah,
it
sir.
visible?
Is visible, sir. But can you just zoom it, if possible? Slightly zoom it. And of course, we're also sharing this list on WhatsApp. No hurry. By evening also, you can check it. And even after the delivery of certificate also, if you find any mistake that has come into your certificate, we'll rectify only once. Okay. So that chance also we are giving from organizer side. So please. Thank you. Over to Vijay Kumar.
Sir has joined, sir.
Probably he'll come, sir. He'll come. Or can you contact him? Just so that Madam will present vote of thanks.
Devendra sir, you just scroll it.
Sir, already I have forwarded in the chat box also, sir. The link has been provided.
Okay, right.
Okay,
right.
okay.
Dear participants, now we have with
Hello,
us.
sir. Sir, will you please join us?
Internet is down. I am trying to connect it.
Okay, sir. We will wait, sir. No
we'll
problem.
wait.
Yeah.
Yeah, before that, now we have joined in the evening Dr. P. Himabindu ma'am, faculty Nizam College, assistant professor and coordinator of IQAC. Madam will present word of thanks on behalf of organizers. Over to you, ma'am. Let sir join and then you can just.
Shall I wait for him to join?
Yeah.
Yes, madam.
He's
One
joining.
minute. Sir is trying
He's
to
joining.
connect us. Devendra sir.
Sir,
సంతోష్ కుమార్ సార్ వచ్చారు ఒక్కసారి చూడండి
unknown, sir.
ఒకసారి కో హోస్ట్ పర్మిషన్ ఇవ్వండి
Sir.
Vijay Kumar sir, I have a request from participant side.
సార్
Since they are listening to talk since almost 2 hours,
ఎస్
most of the participants asking 5 minutes break at least.
ఓకే సార్ నో ప్రాబ్లం
After madam presenting vote of thanks, and we'll just break for 5 minutes.
ఓకే
We'll be on online only. We won't disconnect it.
రైట్ due to poor internet connection, sir has disconnected.
And shall we go with the proceedings with the ma'am, and maybe meanwhile, he'll be joining.
Turn his call him. Keep your loudspeaker on.
Keep loudspeaker on, and then he can listen to the voice at least, so that he'll. And you keep your loudspeaker also on. మేడం మీరు కూడా అది అచ్చా మీరు అవసరం లేదు, విజయ్ కుమార్ సార్ పెట్టేస్తారులేండి.
సమాధానం ఇవ్వడం లేదు.
Sir is not lifting the call.
Ma'am, then you go with the proceedings. And with anyhow we are recording, no, we'll send the recording video, and sir late he'll watch it.
Right. Good evening, everyone. And at the outset, I would like to thank the organizers for giving me this opportunity to thank our speaker, Dr. Srinivasan Anandan from ARCI.
Yeah, sir is joining.
Shall I wait?
No, you continue.
You continue.
Yeah.
Yeah, John.
First of all, I was very much fascinated to learn about the history of lithium-ion batteries, like across the world, how it started and how it is going in the current day and all. And he has also clearly explained the operating principles, applications, and how different cars are using these batteries, and most relevantly about the EV technology or the electric vehicle technology, which is there, which can be used for saving money, and then also to reduce the CO2 emissions, which is the need of the hour because of this global warming. And he has also very well explained about the foreign import. I mean, the expenses which are incurred because of the foreign import, and also how we can cut short all the expenses by manufacturing on our own. So he has also asked us, or he has given a call that we have to develop cost-effective materials, and very well explained about the lithium iron phosphate. So that was so good. So he has differentiated the capacitors and the batteries, and also he has given examples of few batteries which are working. And he has also given a call that India, our country, needs an alternate battery research, alternate battery electrode material research. And I'm very happy that ARCI is doing such wonderful research, which is in our own place, which is Hyderabad, which is a proud thing for us, because all the world is looking at alternate energy devices, and ARCI being part of that, obtained many patents on that, and they have also filed few patents. I have seen the list of patents which Dr. Srinivasan Anandan had. He has 15 patents, and he has also said that we have to focus on so much of material synthesis which has high performance, low cost, and high durability. And I personally felt that this presentation was very much suitable for the students, and it was also understandable by everybody, like both physics and chemistry students and faculty, everybody could understand that. So his presentation was very neat. Sir, we are very thankful to you. If you are listening to me, I would like to personally thank you on behalf of Nizam College, our organizers, participants, and also the faculty. And the thing which he told about the development of porous carbon from from waste, bio waste, that is really, really interesting, and it's very useful. The application is very high. It is so good because we have so much of bio waste in our country, and the use of bio waste for producing carbon with high efficiency, like they have produced something like 65% efficiency carbon. That's superb. And we are fortunate to learn about what's happening at ARCI and how carbon is being produced. Sir, we are thankful to you, and also for the supercapacitor cell fabrication, which you explained clearly. Thanks a lot. Thank you, sir.
Thank you, Himabindu Madam, for presenting the vote of thanks to Srinivasan Anandan sir. And on behalf of organizer, once again, we are thank you very much, sir, Srinivasan Anandan sir, and joining again even after the interruption. Thank you, sir. Over to Vijay Kumar sir.
Now I request Dr. K. Ashwini Madam to present a certificate of appreciation to our speaker. So
Sir, am I audible, sir?
Yeah, yes, madam.
Sir, Srinivasan, sir. Good evening, sir. Thanks for enlightening us on lithium-ion batteries and superconductors and the indigenous techniques which ARCI is trying to develop. from the organizers, we would like to extend a token of appreciation in the form of a certificate, sir. Please kindly accept our appreciation certificate, sir. And thank you very much, sir, for being with us at this time. And we really enjoyed your lecture, sir. Thank you, sir. Thank you very much.
Thank you very much, sir, Srinivasan Anandan, sir, for accepting our invitation in a very short time. If any inconvenience from our side, please excuse us, sir. So thank you, sir. Thank you so much. Thank you, sir.
Vijayakumar sir, 5 minutes.
A 5 minutes break, then we will join for next session. Next speaker, Dr. Santosh Kumar from UK.
Yeah, next speaker is also ready. So some participants requested us. So we'll be breaking for 5 minutes. Thank you.
Dr. Santosh, can you hear me? Devendra sir.
Sir.
Yeah, Santosh Kumar unnar kada.
No, sir.
Can you hear me? Yeah. Good evening, Santosh.
Can you hear me?
Yeah.
Yeah, good evening. Yeah, it's still morning for me.
Voice betterment.
So, your voice is a little bit very slow.
Is it low?
Yeah, sir. You raise the volume.
Yes.
Let me increase the volume then. Just give me a minute. Fine from my side.
Yes, sir. Now it's okay. Yeah, now it's okay.
Is it okay?
Yeah, okay.
All right, that's great. Yeah.
Hello, good evening, sir. This is Upender from Physics Department.
Hey, yeah. Hi, Upender. How
Hello,
are
sir.
you?
Fine, sir. I'm doing fine.
Good.
Santosh, can you share your screen, please?
Oh, yeah, sure. Give me a
We will
minute.
just check it once.
Yeah, no problem. Give me a minute. Right. Can you see now my screen?
Yeah. It's
Yeah,
clear.
okay.
It's okay.
Clear?
Yeah, but your voice is very low. Can you improve a little bit?
Maybe, yeah, I can maybe let me take off. It is good. How is now?
Now it's
Yeah,
coming
okay.
good. Now it's
Now it
coming
is
good, sir.
Now?
Yeah, it is good now. So just 2 minutes, we will join. Just 2 minutes break.
What do you think? Like without my headphone or with headphone? Which is good?
With headphone, it seems good, sir.
Okay, then great. Yeah.
Yes,
So
okay.
go,
Right.
let's go.
Since
with it.
participants are
maybe,
requested for
maybe yeah, maybe during presentation. So obviously, I have a loud voice anyway. Don't worry. So okay.
Good.
But now we are talking. So it's maybe voice is low.
Santosh, just 2 minutes. 2 minutes, we have given a break.
No problem.
Yeah, you can talk
I'm
to us,
just-
sir. No problem. You can talk to us. We can interact.
Yeah, I'm just having interaction with you. So,
That's what. So
that's
since the earlier lecture began at 3 o'clock and it almost ended just only 5 minutes ago.
yeah, that's absolutely fine. I've been here. I've been hearing you. We have been late for 15 minutes. Yeah, that's absolutely fine. I'm okay. I mean, I'm the last, so there's
No, there is no other
rush.
speaker to be
There's
waiting.
no
Yeah.
rush. And
No,
I can
you
adjust.
have any time constructions there?
To be honest, today I'm okay. I'm free.
What is the time now, sir? There. What is the time now?
Time here is now 12:30 afternoon. Like yeah.
Oh, afternoon. No, it's okay.
Okay, so then it is no problem.
No,
for
no
us.
problem.
it's absolutely fine. Because more or less, like nobody is working from office. To be honest, most of them are working in the lab, are not allowed into office space. So it's fine. So it's quiet.
Okay.
And let me introduce the participants also, sir, to you. We have a cluster of chemistry, physics, faculty members, senior faculty to junior faculties, and faculties from various engineering colleges and various government degree junior colleges, and participants like research scholars from different universities of the country, and few students also joined from different PG colleges.
That's great. That's great.
That's
That's what I've been observing as well. I mean, I heard from Dr. Vijay as well, but now I realize after hearing some of the talks because the wide range of audience. So
and even I request from this platform that if you can throw some light on the opportunities that youngster can have in UK, and that maybe in the end you can just throw some light on it.
Yeah, definitely. I will. I mean, I don't have slides on that, but I can.
Just
speak
orally
about
you can.
that.
Just
Yeah,
orally.
exactly. exactly, I can do that. And then also I'm trying to keep it, as simple as possible. I don't want to go into too much science, because looking at the wide range of audience, because most of them may be not aware or not working, but yeah, I will try to keep it simple and try to test some basics to make them understand at least. So I will do that. Yeah.
That's great. That's great, sir.
So how is things in Usmania? Are you working? Or
Now we are right now. Currently, everything is locked down under Usmania.
It's really challenging for students, particularly.
Yes. The students are on
because
frustration mode.
I know engaging students through virtually, it's something, it's challenging.
Especially this pandemic playing a very a damaging role in the final year students' life.
Exactly. A lot of opportunities that would be missing.
Yes, linking with the certificate, final exam certificates.
Exactly.
UGC.
Even like if they want to do further, the higher education in their careers, so there are a lot of opportunities now locking, because of this pandemic issue. That's something.
And they're at the verge of losing one very crucial year, since it's already September. If we are unable to complete exams within a month, and they are definitely going to lose one important year in their career.
Exactly. And then also like in terms of funding, to be honest, like coming days will be more worse than now.
Yes.
A lot of funding will be cut.
Yes, financial crisis is also.
Yeah, exactly. That would,
And first and foremost, government looks for a research funding, cutting the research funds, basically.
Yeah, that's what's going to happen, in every field. So they're going to cut a bit,
Right.
They don't cut 100%, but but everywhere it will be, cut some funding. So then that makes.
First, government look into education sector, even though they are not giving any huge funds, but whatever the funds they are sharing with us, and they look for that. And
yes, forget about developing countries. Even developed countries are struggling with this. We like here in UK, we had a lot of fellowships opens earlier. So now one by one, slowly, they are, time being, they are stopping. That is what's happening now.
Yeah, over to Vijay Kumar, sir.
Yeah, shall we start, sir?
Yeah, I'm okay.
Yeah. So very happy to see you, Santosh, after a long time.
Yeah, me too. It's nice to connect and meet particularly students and talk to them. It's always joy.
So thank you very much for accepting our invitation. So
That's
now I request our head of the department, Dr. B. Sakram sir, to introduce our speaker. Dr. B. Sakram sir, over to you.
Hello, Vijay sir. Hello.
Yeah.
I'm audible, sir?
Yes, sir. Please.
Yeah. Good evening to you all the participants and today's speaker. It is a great pleasure to introduce today's speaker, Dr. Santosh Kumar sir. Dr. Santosh Kumar sir is currently working as a senior research associate at the Department of Chemical Engineering in Imperial College, London. Sir worked as a PDRA at the Energy and Bioproduct Research Institute in Aston University, and earlier also at University of Bath. Dr. Santosh is skilled in functional material design and synthesis, surface interface engineering, carbon dioxide utilization, and photocatalysis for solar fuel production and environmental remediation. Sir completed his PhD degree in the area of functional nanomaterials for clean energy and environment at the NIT Warangal, India in 2014. Prior to joining in PhD, Santosh sir was awarded a lectureship by CSIR UGC NET India in June 2008, and he worked as a lecturer at Sardar Patel College under Usman University 2007 to 2008. He also worked in industry as a R&D chemist in Saffola Organics Private Limited, Hyderabad. He has published more than 35 research articles with good impact factor and 3 books chapters with more than 2,500 citation, and his H index is 21. Dr. Santosh is a fellow of Higher Education Academy of United Kingdom and a member of the American Chemical Society, the Royal Society of Chemistry, Green Chemistry Network, UK Solar Fuel Network, Carbon Dioxide Chemistry, and International Association of Advanced Materials. And Dr. Santosh sir reviewed more than 30 research articles like elsewhere for highly reputed journals like Nature Scientific Review, American Chemical Society, Applied Materials and Interface Materials Today, Applied Catalysis and A and B, Physical Chemistry and Chemical Physics. Now I am thankful to you organizers to giving me this opportunity. Over to Santosh Kumar sir.
Thank you, Dr. Ram, for your kind introduction. Let me start with thanking organizers, particularly Dr. Vijay and Dr. Upendra, for giving me a wonderful opportunity to share my work and also share my some of the thoughts about the career with you all. I mean, particularly students who are interested. Today's talk title is Engineering Nanomaterials for Solar Fuels via Artificial Photosynthesis. But I will be touching also a bit of introduction about the photocatalysis, because looking at the wide range of audience who may not worked or heard about the photocatalysis. So I thought like giving some introductions, and then I will move on to solar fuels and some, current research activity I've been doing at Imperial, or I did previously in Bath or Austin University. So my research activities, particularly clean energy and environment center. So one of the major area I focus on is making functional materials. And recently we also started developing a green synthesis methods for making these nanomaterials. And another area is the application, that is particularly photocatalytic applications for solar fuels and environmental remediation. For example, you take a solar hydrogen production, and also you can convert carbon dioxide into various low carbon fuels. And then most interestingly, the biomass reforming, Today, algae as biomass, algae as looked, or even rice straws, for example, we are the country where we produce a large amount of rice. The rice straw will be wasted, burned out, and which is emitting the carbon dioxide, and which is responsible for one of the chemical responsible for the global warming, right? So these biomass can be turned into useful low carbon fuels using solar energy particularly. So, and then most importantly, I will be stressing a bit on surface science. So this is where we interested to understand how it works. If you take a particular process or a reaction, how it works and what it happens, and what need to be done to improve the efficiency or selectivity towards a product. So that is where being a chemist, we are a researcher, we are interested in.
Santosh, can you little bit improve your voice? Little bit.
Right. So is it okay now? Yeah.
Yeah.
All right. So yeah, so that I can. I mean, yeah, that is where we are interested in surface science. So yeah, if you want to look into my research activities, so what you can do is Google my name, or with this link, you can see my profile if you want to see the activities, or if you have a question, or if you want to work with us, you can get in touch. That's absolutely fine. We're always happy to collaborate with the new people, or work with the new people, or share our knowledge. So, and then also before jumping into the work, so let me introduce where I am from. I'm basically from India, but professionally where I am from. So this is where the UK is located. So, and then if you see the London is down in the corner, and then the Imperial campus is in the center of the city. So it's one of the very attractive tourist place, that's Hyde Park. It's just next to the Hyde Park. And then we have a range of facilities in terms of analytical facilities. And also, we have a CO2 capture plant, pilot plant. So where we capture the CO2 and then that can be converted into useful low carbon fuels. So that's what we've been doing at Imperial College. So that's great. So we have been doing okay, that's great. But why we have been doing? What is the motivation for this? That is because you don't do something without the need of without the need for that to do, right? So what is the motivation? So particularly for me, the motivation is our day-to-day life challenges. Look at the environmental pollution. So after the Industrial Revolution, the human activities on Earth has polluted, including air and water and even soil, right? So this is and this is the time. So we need to reflect ourselves and act. If you see the carbon emission level over the years, it's very high. It's keep increasing steadily. So this is an alarming situation, right? So on other hand, and today we are facing another challenge, that is COVID-19, right? So there are challenges which needs to be addressed as soon as possible. Otherwise, we will be facing another pandemic like COVID-19. Another motivation is the energy demand. A rise in population and the change in the lifestyle has drastically increased the consumption of energy, right? So, on other hand, we are polluting the air. So we need clean energy. So moving to a clean future by decarbonization of transport and other industry through the renewable is the key. So what is need to be done for that is to look at alternate strategies which can fulfill our energy demands and protect our natural environment. That is what needs to be done, right? So, and for this, what is my approach? So my approach is semiconductor photocatalysis. Right, so you may ask a question, why do you think semiconductor photocatalysis helps in this case to address these challenges, right? So, because the semiconductor photocatalysis is a pathway from sunlight to clean energy and environment. And this process fulfills the most of the green chemistry principle. We know there are 12 green principle of, 12 green chemistry principles, and this process satisfies most of them. And look at the application. Look at this figure, and it has a wide range of applications. So that is where it matters. So if you look, for example, using this process, you can purify the air, and you can, and also another, you can, you may be familiar already. Some of these photocatalysts being used in self-cleaning glasses. And also we can produce, I will be talking some of these applications I will be talking in detail, but I'm trying to give an overview of these applications of this process. So, and one of them is solar cells. So this is where the light is playing a role here. So you've been hearing on solar cells for the last 2 days, right? And water purification. You can have a catalyst which can take the light energy, basically solar energy, and can purify it can degrade the impurity in the water and give a clean water. And you can also construct a bricks, with these materials, particularly for the so-called photocatalyst, so that can, clean the walls and keep you, away from the pollution. And then also you can like sterilization, for example, you can like a lot of microorganisms. They've been used in the hospitals. There are a lot of microorganisms associated with these equipments. So you can you can clean them using solar energy and so-called photocatalyst, right? And also deodorization. Any odor can be degraded. So these are the applications, so which motivates us to look into photocatalysis process. And right, so there are plenty of applications, as I said, but what is the current state of art in this area? This is a slide, is very important to look at. If you see, for example, one of the application that is self-cleaning glass surfaces. You can say self-cleaning glasses. And also air purification. Self-cleaning glasses has a mature market, as you see, as I label. But look at the air purification and water purification relatively is better. It has a like market entry at least, but still there are a lot of challenges associated with these materials. Particularly for these applications. And solar cells, it has a mature market, and as well as the actual research at applied stage to improve the efficiency and bring down the cost, right? And mainly what I am interested is the top two applications like hydrogen production and CO2 and biomass conversions into useful low carbon chemicals for the petrochemical industry or even transport industry. So this is still at basic and applied research. So what I will be aiming for is to get that position, at least a market entry, right? That would be great, even next 10 years. So, but okay, that's great. So there is a lot of opportunities and in this area, but what is photocatalysis? That's something for because looking at a lot of a lot of people in the audience are very new to might be new to this area. So let me tell you what is in brief, what is photocatalysis, what is particularly semiconductor photocatalysis. It's basically, it's a light driven heterogeneous catalysis. You may be familiar, some of you might be familiar with the heterogeneous catalysis. What happens on the catalyst surface is the reactant approaches the catalyst surface and settles onto active sites. That is what we call adsorption. And another reactant approaches the catalyst, and then there is a rearrangement of electron that is called reaction, and then the product will be released from the surface. So that is desorption basically. So in photocatalysis happens the same thing, but in the presence of light. What light does here is, so when you irradiate a so-called photocatalyst or material, the semiconductor, when you irradiate with the light energy, which is equal to its band gap energy or higher than its band gap energy, so it generates the electron and hole. Well, let's say this is the bottom one is the valency bond, and top one is the conduction band. So when you irradiate with light, the electron from valency band jump to the conduction band, and you have an electron hole separated. And these electron holes, if you want to look at in the details, let me go to next slide. I will explain in detail in a stepwise. You can see here. So the first step is the photon absorption. As I said, so when you irradiate it with the light energy, which is equal or higher than its band gap energy, so there is a light absorption. And then in second step, what happens is the charge migration to surface. So these the electron, the charge carrier, that is electron and hole, in the electron in conduction band, hole in valency band, migrate to the surface. That's the second step. And third step is the redox reaction. That's the simultaneous oxidation and redox. So where on surface, the electron undergoes the reduction, whereas hole undergoes the oxidation. So there is an unwanted another step, that is recombination of these electron and hole pairs, this charge carrier recombination, so-called charge carrier recombination. So this is unwanted, and it happens by combining the electron in conduction band back to the hole in valency band by releasing its energy in the form of heat. This simply wasted photons, right? That is, we don't want. So that is where the chemist role comes, place to improve the stop it and improve the efficiency of this process. So some of the example, for example, let's say solar fuel, as I said, like solar fuel production, that is hydrogen production. This is how it works. The electron react with the water and produces the hydrogen. Basically here proton is undergoing the reduction. And then whereas the hydroxy ions undergo the oxidation and produce you oxygen. And in for example, another application, if you take water purification, what happens is the electron can be trapped by oxygen in the atmosphere and produces superoxide radical, which is a oxidizing agent that can degrade any kind of organic pollutant, or you can convert even convert the inorganic pollutant, harmful inorganic pollutant, into a less harmful or unharmful chemicals. So whereas like a whole directly can react with these organic species, or you can react with the water, OH, and produces hydroxy radical. This is hydroxy radical is a strong oxidizing agent, can break down into any kind of organic molecule into a small pieces, unharmful species, I can say. So let's see what not only like water and hydrogen. So there are many applications in environmental remediation, including indoor and outdoor. So if you mix these catalysts with a paint, that can degrade in the mold, particularly developed countries or cold countries. That is a challenging issue, and also a lot of other toxic gases within like small organic molecules, formic acid, or even formaldehyde. These kind of molecule can be degraded into unharmful chemicals. So not just that, I will be talking about even COVID, how the photocatalysis could help to mitigate the COVID challenge. I will be talking in the next slide. So as I said, like how it works for the water purification. So as I discussed, so you have a separation of electron and hole, and these will react with the oxygen. The electron will react with the oxygen to form a superoxide radical, and then whereas hole react with the water to produce a hydroxy radical. So these radicals are powerful oxidizing agent, can mineralize any kind of organic or other pollutant to less harmful, or even water and CO2. So as I said, like so not only just like water, and also like other applications. For example, this is one of the challenge in transport industry, so which is producing a nitrogen oxide, which is very harmful, which is the reason for the the pollution in the air. So if you make a brick, if you embed the photocatalytic material in a brick, so that can use the moisture or oxygen in the air at the same time and absorb the solar light, can convert this nitrogen oxide into a less harmful nitrogen oxide, that is NO3 minus. So there are potential opportunities in this area, but there are also challenges. So that is where so as being a researchers, our role counts to address the challenges, so make it happen. So as I said, so another area of application is biological applications. So biological application is, for example, as I said, you can take a COVID-19, but there are a lot of pathogens, right? Microorganisms, right? So if if you coat these material, this so-called photocatalytic material on any hard surface, so that can under oxygen, and even it should, but yeah, of course it should work indoor light as well, outdoor and indoor light. There are challenges, as I said, so I will be discussing later on these challenges as well. But let me give you the the beauty of this photocatalysis, the application of this photocatalysis. So if you coat on the hard surfaces, it might be a hospital or your office or our desk, it might be our desk, right? So what it does, as you learn previous slide, it produces these strong oxidizing agents, right, under light and in the presence of moisture and even oxygen. So these powerful oxidizing agents can break down any kind of big molecule, organic molecule, even COVID-19, right? So then, particularly it may not be bring into a CO2 water, but it can be bring into a smaller molecule. But this is something new. This can be understood. This can be studied. So there is a lot of opportunity in this area, particularly looking at the current pandemic situation, right? So, there are it's not that there are there is no product in the market. There are products in the market, but there are challenges at the same time. And as I said, not only hard surfaces can be coated on the soft surfaces. That might be your cloth, your dress, or that might be your mask, or can be have a purifier, a filter with a purifier in the hole, that can suck the particles in the air. And then, for example, this is how look at this game. So you can see this small clip here. So if you coat on the the porous material, for example, let's take a carbon. If you coat these these photocatalytic particles on a carbon, so then that can suck the. If you have a fan, so that can suck these particles and under light, so it generates this oxidizing agents, as I discussed, the principle of photocatalysis, and they can degrade into a less harmful the chemicals. Eventually could be a CO2 and water, right? So this is another opportunity in this area. So what I will be more focusing today is this is clean energy application of photocatalysis, right? So here I'm saying it's a clean pathway from sunlight to chemical fuels. The reason I'm saying is, look at the inputs required for this process: sunlight, abundant materials such as water and carbon dioxide. And it might be all biomass like algae or rice straw. And if you look at the process is very simple. It's basically we are copying our nature. Nature knows much before us. So that is photosynthesis. What does happens in photosynthesis? Simply, so the carbon dioxide, we produce can be converted. Basically the leaves in plants can convert that carbon dioxide in presence of light and water into the food. They make food basically. So why can't we copy this process where we can copy or make a material that can copy this process, can do the same job for us, right? Similarly, let's say have a nanomaterial or a material that is so-called photocatalyst. So that can absorb the carbon dioxide and water, and in presence of light can convert into useful chemicals that can feed our industry, right? So for example, if you look at the products in this process, one of those is hydrogen that directly can be used as a transport fuel in industry. And other possible products like low carbon products such as methane and carbon monoxide and even methanol, it could be a raw material for various industry, even for petrochemical industry, right? So, but what are the challenges? And are there any material that can do this job? Yes, there are plenty of materials. There are range of materials. But but there are challenges as well at the same time. And this chart is very important for particularly students who are interested in doing research in the area of photocatalysis for various applications. So here, not only the material is important, but the position of the conduction band and valency band is important, also important for the chosen application. Let us say you choose you want to work on water splitting. You want to produce a hydrogen from water. So the conduction band minima should be above the 0, and the valency band minima should be below the 1.4 electron volts. So again, is the normal hydrogen electrode potential. So that is the criteria for splitting this water into hydrogen oxygen. Similarly, so it is the same case with the other application. That might be a CO2 reduction. You want to convert carbon dioxide into CO2, then you need to have a certain potential to reduce or oxidize this reactant into a useful product. So, and another challenge is most of these materials in the literature are only active under UV light, right? So, but if I go back to just next slide quickly, if you look at this graph, what percentage UV we have in solar spectrum? Just only 5%, right? So that's not good enough to go scale up or for an industry. So what is important is the material you make, it should be active in visible light. So visible light is almost 45%, which is almost reaching the Earth surface. So the key is to develop a visible light active photocatalyst. If I go back, so here, so one of the well-used material is photocatalyst, is the TiO2. It has a high photostability. It's very low cost, non-toxic. It's fantastic, but the problem is it only absorbs the UV light. It doesn't absorb the visible light. So to improve the performance, there have been several strategies. Basically the several strategies has been applied. Though some of them I listed here, like a metal doping. When you dope with the metal, so what happens is you have another level just below the conduction band, so that reduces the band gap energy, so then it can absorb the visible light. And another option is non-metal doping. For example, if you dope a nitrogen to titania, what happens? It forms a energy level just above the valence band. So that can again brings down the band gap energy, so can absorb the visible light. So there are you can co-dope as well and create our oxygen vacancy. There are a lot of strategies in bringing from UV to visible light active. But what is more important is the surface modification. Surface modification with for example, dye sensitization, what you see in solar cell applications, and also coupling with the metal another small band gap semiconductor which can absorb the visible light. So here two jobs can be done. One, the small semiconductor you're coupling with the, for example, let's take a titania, and let's say copper. You have a copper, it has a band gap of around 2.2. There are different coppers, but let's say copper 1, it has a band gap of 2.2 electron volts, and the titania is 3.2. It doesn't absorb, the titania doesn't absorb the visible light, but copper does. So copper, what does is copper absorb the visible light and excite and generates the electron hole, and that electron can be transferred into titania surface. So here you are making absorb the visible light, and as well as you are separating the charge carrier away for each other to stop the recombination. So that's great. So that's why the surface modification is something can be taken forward for the real world applications. Make it happen. That. So so basically, design and development of robust and visible light active photocatalysts is a key for the clean environment and energy applications, right? So I summarize these key factors and how do we select the catalyst, for the particular application. So particularly in terms of the light property, what is important is, so your catalyst or your material good enough to absorb the visible light. That's something very important. And also it should able to separate those electron and hole. So that these electrons on holes, so maybe I can say charge carriers can participate in a redox reaction. On the other hand, what is important is particularly, for example, like if you want to convert the biomass or carbon dioxide into useful chemicals, so it has to absorb the CO2 on the catalyst surface. So it has to have a large surface area which can accommodate more number of CO2 molecules, and then even lower recombination. High energy surface, that is something important for the boosting the energy of any particular reaction. The productivity of any particular reaction. So having like a basic surface, for example, particularly for CO2 reduction, having a basic surface or a crystal facets that has a high energy can improve the efficiency of this process. So as I said, looking at these factors, and also like as I discussed earlier, the potential, not only the band gap energy, but also the conduction band and the valency band potential matters. So looking at these as I already discussed, this water splitting and also degradation, if you want to form these superoxide radicals or waste radicals, so the valency band potential of your catalyst have to have the minimum that's 2.6 volts against the normal hydrogen electrode. And whereas if you want to produce this superoxide radicals, so the conduction band minimum potential has to have a minus 0.3 electron volts against the normal hydrogen electrode. So as I already discussed about the water. So so looking at these factors and the important criteria for the selections, so what an ideal photocatalyst look like? So this is how an ideal photocatalyst look like. So it has to have a small band gap to absorb the visible light, and compounds or elements with the environmentally friendly, an ability to work without a sacrificial agent. That's something I would be discussing later on. What is the role of sacrificial agent in this process? In this application, like water splitting or maybe CO2 reduction. Long-term stability, that's key for industry for the low-cost device. Low cost, as I said, and high efficiency without expensive co-catalysts such as platinum and ruthenium, right? So most of these reactions work having a secondary catalyst, metal catalyst, which is always expensive. So that having less, expensive or maybe without catalyst, if it works, that's great. And then high yield, right? So you need to produce basically productivity, should be high in production, and then the direct band gap for the better photo absorption. Right. So so looking at these criteria and the key factors, so I have been working on designing and developing various nanomaterials for photocatalysis, such as one-dimensional or zero-dimensional materials of different materials, and also heterojunction, integrating them together to bring these, key factors, basically embed these key factors into a material which can do the job for us. And like even porous material, you can make a porous material and you can deposit on the porous material these nano photocatalysts. And also hierarchical structures. What I would say is not only size and shape, the complexity matters for the efficient photocatalysis for various reasons. We'll be discussing one by one. But that's great, okay, but what is nano? What is the role of this nano? What is nano doing here? So to understand that, I briefly take you through the introduction of nano, and then I will come back and explain so what is the relation between the nano and photocatalysis. So is it nano? Is it a new thing? To be honest, I would not say that, because it's known for 100 years. I mean, for long back. Ancient days, for example, look at this. Have you heard of this cup? This special cup is present in the British Museum. I was lucky enough to go and visit and see this cup very recently. It's called a Lycurgus cup. It's a 4th century Roman glass case. Is made up of a gold and silver nanoparticle coated on a glass, diachronic glass. Is a special glass. Yeah, don't go into the detail, but yes, it's embedded with the gold and silver nanoparticles. When you, it is showing two different lights, right? Red, when light from light shine from the behind, that is transmitter light, and the green when the light is shine from front, that's a scatter light. And also this, look at these pens, beautiful pens. So the red stain is it's because of the gold nanoparticles of 20 nanometers. And the orange is because of the 18 nanometer gold nanoparticles. See, look at the different gold nanoparticles are showing different color properties here, right? To understand this, why it is happening, you need to bear with me for another 5 minutes. So, but okay, so when did I said, like, yeah, he's known for, you know, ages, but when did started the game of nano? So look at the, if you remember this gentleman, he's a Nobel laureate, Richard Feynman, during a meeting, American Physical Society, what he said is, he phrased this, there is a plenty of room at the bottom. What does he mean that? What he meant is, if you focus on building these materials from the bottom, like atomic or molecular level, you can basically do the magic. That's what he meant. You can manipulate, you can control the the material property where you want. That is what he meant. After this great talk, many people like me have inspired by him and started, digging into nano, basically looking at atomic level and molecular level, right? So, okay, that's great. But why we need to look at that atomic or molecular level? Why do you want to, go make into complex? Yeah. But before that, sorry. Yeah. So before that, let me simply define what is nano. Nanometer is 1 billionth of a meter. It's out of our head, right? You can't even imagine how small it is. But let me, as Charissa discussed, he has pointed out, let me visualize. Take a one baseball bat is a length of 1 meter, right? And then what you do is divide with 1,000 or 10,000. So you get to the size of 100 micrometer. That is similar to our human hair, the diameter of human hair. I'm not talking about the length here, but the diameter of the human hair. So this is the size one can see with the naked eyes, right? And look at here, again, what you do is you divide with 10,000, right? If I'm wrong, yeah, so you need to do 10,000, yeah, 10,000, I guess. 1,000, sorry. If you divide with 1,000, you get to the size of 100 nanometer. That's the size of virus. You've been hearing about the COVID, the size of the COVID you might be. So that's somewhere around 100 nanometer, right? So yeah, there are the drawback of this nano, but nano is known for ages. And now let's divide again with the 1,000, and you get to this size of 1 nanometer. Sorry, 100, and you get to the size of 1 nanometer, right? So that's the half of a DNA. So this is the range, the scale range is typically called nano. And there are various type of nanomaterial, nanoparticles like quantum dots, nanodots. Look, they are, if you look at the circlings in shape, and there are nano seeds. The seeds of, in zero, they are all dimensional in nano size. But if you look at nano seeds, so two of the dimension in nano, but not one of them. And if you look at the rod, yeah, you can see one of the diameter is in nanoscale, so that's why they call 1D nanometer, and the nano seeds are called 2D nanometers, and nanowires as well. So even the aspect ratio of length is higher than the nanorad, so that's why they call nanowires. They look like a wire, so they are called nanowires. So these are some of the examples of nanoparticles, how they look like. And right, so as I said, like why nano? Why are we so crazy about making things particularly smaller and smaller? Yeah. Years ago, look at this the left side picture. Years ago, the computer was look like this. It's occupied a whole room. Today we have in our hand or on our desk. It's tiny. Okay, I understand that. It is lighter, it is faster, it is cheaper, and it is very smart. But is it nanotechnology and nanoscience is all about making smaller or smarter? For us, is this what happens at nanoscale? Why we are so crazy? So this is what, being a researcher, we are interested, we want to look into. Already Charisar has pointed some of these like magnetic property or even physical properties, but I will take you through briefly into chemical property and optical property, how they change at nanoscale. So let's take a gold, the best example, gold. The gold we know is, we love it because the reason is it doesn't react to atmosphere, right? But being a researcher, being a person, I may be excited at this call, but being a researcher or a chemist, I'm not fancy about this call because it doesn't react with, it doesn't do anything to me. The bulk gold melts at more than 1,000 degrees, right? And then does not react with, as I said, air and water. And the color of this gold is yellow. But look at this picture. This is also gold. These are gold nanoparticles. I am saying it's a gold nanoparticle. But why does it look like red? Gold we know is yellow, but it looks like it looks red. And it's melting. It melts even at room temperature in some cases, and does react with the air and does react with the water. Even it can split the water and produce hydrogen. Can be used as a transport fuel in industry. And the color, as I said, in red. What happens? Okay, let's understand what are these unusual properties at nanoscale. What is the origin of these unusual properties? What is happening? So one of them is surface to volume ratio. Look at, there are two types of sugar here. One is a granulated sugar, another one is sugar cubes. Which one do you think melt faster? It's obvious, you would say the first one, that's a granulated sugar. Because the value, I mean, the bulk to, the surface to volume ratio is very high. So let's understand this with a small example. See here, I have a cube of 2 meters, and another, I break down into 8 pieces, and they each, I make it into half, both side way. And then if you see and calculate the surface area, is in first case is 24, in second case is 48. But calculate the volume as well. Does volume change? No, volume is same, right? So, but that's why the surface to volume ratio has increased. So, and here, this is where the chemist is interested, and they are excited as well. So what happens when you have a high surface area, the large number of reactant molecules absorb on the surface and react faster and improve the efficiency of any reaction, or rate of any reaction, right? So another important property is the unusual property of this happens at nanoscale is the quantum size effect. Basically, the difference is, as you see in this picture, on the left side picture here, so from red to green is the same goal, changing the size of the goal, they have a different color. So the different size of goal, basically here, absorbing and reflecting different light due to the quantum size effect. What does this quantum size effect? What does it mean actually? So you may know, so semiconductor has a valence band and conduction band, or if you take a gold, a metal, any metal, so you have, you know the electronic arrangements, right? The energy levels. The highest occupied orbital known as a HOMO, that is valence band, right? And then the lowest occupied orbital known as a LUMO, that is the first unoccupied orbital. And usually in metal, you learn there is no gap between. That is how we classify metals, semiconductors, insulator, right? So there is no gap between, almost zero gap, you can say, between this valency band and conduction band, that is HOMO, LUMO. So what does it mean is the electron in metals are free to move. They are free of motion. They are roaming around. So when you break down these metal particles into smaller smaller particles, so what happens is there is a splitting of these energy levels. Why does this split into energy levels? Right? This is where the quantum chemistry or quantum physics comes into picture, right? As you know, according to the classical physics, what you know is the Bohr model, or you can simply say the Bohr model says the electrons are roaming around the nucleus in a certain path. But that's the classical mechanics or classical physics. So what quantum physics says, that's not true. I don't agree with you. So what quantum chemistry says, Schrodinger equation, or you can say, if you go into detail, what it says is it does rotate around the nucleus, but it doesn't has a particular path. It occupies a certain space, that's so-called orbitals, right? So when you break down into, what you are doing is you are restricting the movement of these electrons. So basically, in a clean word, what I would say is the electron's motion becomes more confined than before. So in a simple word, if you want to understand, they squeeze each other. Okay, the energy levels squeeze each other and create a gap. that is called energy gap, or you can say a band gap. So these metal can act as a semiconductor in nano. That's strange. We never learned, right? So that is the reason. So when they act as a semiconductor, so when you shine a light, this energy gap will absorb or reflect light depending upon the energy gap. I mean the energy of that gap. So that is what happening in the case of gold nanoparticle, which are embedded in this Lycurgus cup. So they have a certain size. So depending upon their size, there is a gap. They have a certain energy gap, and based on that gap, the energy, it is, the electrons are in resonance with a particular wavelength of light, and then absorb that particular wavelength or emit that particular wavelength. So that is why you are seeing a different light, right? So, okay, how do you make them? How do you make these nanoparticles and nanomaterials? I don't want to go into each individual procedure, but what I can classify is there are two different approaches. The one is, that's the you can say bottom-up approach, and then another approach is, the second one is the top-down approach. So what happens, what does it mean, the top-down approach? Top-down approach is like a carving a big rock into a beautiful piece of art, or statue, you can say. So that's the top-down approach. What is bottom-up approach means is, you are starting with the reactant, molecules at the molecular level, and you building them together, and you growing as you want into a nanoscale. So that is what called bottom-up approach. Sorry. And so for example, this is what we do in our lab, a mechanochemical method. So when you have a ball and ball, and you add the bulk material and you grind them, and you break down them into nanoscale. This is called top-down approach. Then another example we do in our lab is a wet chemistry method, basically wet chemistry. For example, here, copper nanocubes. I can make a copper nanocubes adopting this bottom-up approach. I have a copper chloride here, and I add some base to it to activate the copper chloride, and I use a glucose as a reducing agent. It reduces the copper 2 into copper 1 because I want copper 1 here. So I give a certain energy. That's what I'm doing here. I'm heating up, and you see beautiful cubes, well-shaped cubes. This is called bottom-up approach. Not just this, you can make a range of materials using different methods. There are plenty, range of wet chemistry methods. You can make integrated materials or co-cell, like for example, one of them co-cell. Co-cells are very well known for drug delivery. So depending upon the application, so you choose a method to make them. Come back to the relation between nanotechnology and, so you know what is nano, what happens at nanoscale. So how the nanotechnology or nanomaterial related to photocatalysis, or what is the relation between these two? Basically, the catalytic behavior is not only strongly material dependent, but also extremely size dependent. The quantum confinement and surface phenomena based on particle size dominate material properties at nanos level, as we discussed. So in photocatalysis, what we have is low surface area, is give you abundant reactive sites, and by reducing the bulk to surface distance, the electron can reach surface quickly and reduces the recombination rate and absorb the light. For example, the gold plasmonic nanoparticles. They absorb a different light depending on the size. And you can tune the band gap, the quantum size effect. Because of the quantum, you can adjust the band gap energy. And prolong the lifetime and stronger reducibility because of the high surface energy. So these are the advantages of this nanotechnology in photocatalysis. One of the known photocatalysts is TiO2. So for actively used, it has been used for several years, even decade. That is commercially available is called P25, has two different phases. One is rutile, one is anatase. Is widely used as a prototype, even prototype photocatalyst in these applications. The reason is there are some advantages as listed. Wide band gap, high photostability, low cost, non-toxic. These are key. And as I discussed earlier, it doesn't absorb the visible light and poor charge separation, and only works under whole sacrificial agent. Remember the whole sacrificial word here. So I will be discussing later on. So therefore, the designing the visible light active catalyst is the key. So what we did, particularly me as a PhD student, or even during postdoc, always we start with the known thing. So I started with titania, but what we wanted, looking at the advantage and looking at the future perspective, so it was not working for me. So what I did is I combined with the layer hydroxide. So these layer hydroxide is a 2D layer anionic clays. It's very cheap material and readily available and environmental friendly. But what is the beauty? The beauty of this material is they have a right band gap and they can absorb the visible light. And they are very good for oxygen evolution, particularly oxidation, the other half reaction to complete the redox reaction. So what we did is we combined, integrated together with the P25. I started with the commercial material first, that's P25, titania. We integrated nicely, you see, and then we tested them for CO2 reduction particularly. So when you have a pure titania, the activity is very low. You can see the first on this graph, very low. The reason is one of the reason is it doesn't absorb the visible light, and also the poor charge separation, and its high over potential to complete the redox reaction, the second half, that is oxidation. Yeah, as I discussed earlier, to complete the redox reaction, it has to happen reduction as well as oxidation. The reduction is, for example, in this case, the electron in conduction band react with the CO2 and produce the, for example, carbon monoxide as a fuel, carbon as a product, you can say, just simply. And then whereas the reductions has to happen as well to happen the reduction, so oxidation has to happen as well to complete the reduction. So that is in general, what people do is use the sacrificing agent, so-called scavengers. For example, one of these methanol. If you use methanol, what does methanol is? It reduces the, it converts into formic acid, formaldehyde, formic acid, and then even CO2. But what I'm trying to tell you is, it completes the oxidation by reacting with the hydroxy and then convert some other product. So then the other half reaction, so your holes are consumed, so the electrons are free to participate in the reduction. So then you can reduce the CO2 into here in this case carbon monoxide. So that is where so here, but when you use like this kind of whole scavengers, additional reagent, it's not an industrially feasible process, right? So it brings a lot of things into picture. improves the cost, increases the complexity, right? So what we did is we combined with this layer hydroxide to complete this oxidation. So look at when we combine this with titanium with layer hydroxide. So on layer hydroxide, they have an potential to reduce the oxygen, water to oxygen. And then whereas on titania, the electrons on titania can react with carbon dioxide to produce the carbon dioxide. So you're basically completing the redox reaction without using any additional reagent, so-called sacrificial agent, or you can call scavengers or reagent, whatever it is. So, and yeah, we achieved the extended light absorption and even CO2 absorption because these layer hydroxide is very good for CO2 capturing. And selectivity, that is something the industry will be looking at, selective production of any product they want. The selectivity is higher than greater than 90%. So then what we did is, okay, the layer hydroxide is a bulk, although it is a thickness of nanometer, it's in nanoscale, but it's still a bulk layers. You have several layers, and I reduce into a few nanometer thickness. Then I combine back with the titania. This time what I did is a specific size, particular size, 8 nanometer nanoparticles, and with a similar size of different titania. I played with the titania structure as well. Let's see whether this is safe is affecting here. We know nano, from bulk to nano, it does, but also does the safe effect. So I changed this, I kept the same nano seed, the layer hydroxide seeds, and deposit different shape of same size. Remember, they both the diameter of particles and nanorods are same here, right? So then you see here the activity. Here the last one is the highest activity is with these nanowires on these layer hydroxide seeds. The reason is here in these two cases, here these are like a point, the particles are like a point, say circle particles, and these are like a rods, right? And you have like a rod and phase interface, seat and rod, right? It's like yeah, you can say like a line and phase interface. And then in case of nanoparticles, it's like a point and phase interface. So the contact area in first case, nanoparticle case, is lesser than in the second case. That is the reason. So at the interface, the contact area is high in the second case. So that is the reason the activity is much higher than these are even put on the pure layer hydroxide or titanium. And the quantum efficiency we achieved is 0.26. That is still very low, but as I said, we're still at a basic level. And to understand this interface, we did some band alignment. What I want to say is, I don't want to go into detail, and also looking at the time. So look at here, these values. In case of titania, it's much smaller. This delta E is much smaller than the nanoparticle. And I mean, the nanotube. Nanotube, we can say the one dimensional. In case of one dimensional, this is much smaller. That is telling you the interface is much stronger, and the holes are migrated quite quickly onto layer hydroxide from titania. In the similar way, the electrons from conduction band of layer hydroxide to titania. That's where you are separating these electron hole efficiently, and they can participate in redox chemistry. So another, like, we can understand that the charge separation, as I said, like you are improving the charge separation, we can understand by the PL emission spectra. So as you see, the PL intensity on this in pure, the pure is the high intensity is the pure, has a high intensity, and after integrating with the layer hydroxide, the intensity has gone down. It's like a flat line. So that tells you the charge, because the PL emission spectra is a result of recombination. So that means you are suppressing the recombination. So that's great. We don't want that step. If you remember, that's the step I said. It's an unwanted step. That's what we don't want to happen. That's we're able to suppress it. So that's something we can understand the science to improve the efficiency of this material. Another material I work, I'm glad to say, when I started, I worked on this material during my PhD, and I'm working in NIT Warangal. But yeah, I feel lucky enough to also do some work in IIT Delhi. But I picked this material. There was no report on this material. I was the one from India to work on, one of the few in the world to work on this material. Back in 2010. So now it's become like a visible light prototype, like a titania is a prototype material for UV active. This material is a UV active, visible active prototype material in photocatalysis. So yeah, so to keep brief, so again, it's like the bulk carbon nitride material. This carbon nitride is a polymeric material. It has very low surface. So I prepared the nanosets, which has huge in surface area, and you can also tune the you can tune the band gap, and you can tune the absorption or emission of the light. So you can play around depending on the application you want to apply. So yeah, so one of the I think I'm running out of time. How much time I have, Dr. Vijay? Can you hear me? Hello?
Sir, go ahead, sir. You can have.
All right. Okay. No problem. Yeah. So I have time, right?
We have 5 to 10 minutes, sir.
No problem. Yeah. So I will wind up in 5 to 10 minutes. Right. So, okay. So, right. So go back to my slide. Did I stop sharing? What's up? Okay. Yeah. Right. So yeah. So and then yes, we try to understand the mechanism. We try to identify what is the reactive species. Like as I said, like whether it is a OH is a reactive, or whole is a reactive, or superoxide is a reactive. So this is something you would be interested because if you know which is active, so you can tune your material based on the application. So I don't want to go into detail. So I will keep moving on to another material I'm working on currently is halide perovskites. These halide perovskites, sorry?
Santosh.
Yeah.
You have 15 minutes more, no problem.
That's great. Yeah, so 15 minutes good enough for me. Yeah, I will wind up. Thanks a lot. Right. So another area of my interest is halide perovskite. Recently has been when I have been working on this material at Imperial here. So as you have been hearing about these materials, they are a very success in photovoltaic field due to their photophysical properties. You have been hearing last 2 days as they absorb the visible light, and you can tune the band gap in a wide range. And they have a high charge carrier mobility that is important for the redox chemistry. So, but what is challenge with this material is here. So one is the complex synthesis. Another one is the stability, right? So address these challenges. What I did is in the literature, people use the wet chemistry and use the ligand, surfactant, lot of reagents, so it makes more complex and harmful to environment. So what I did is I adopted mechanochemical chemistry, basically mechanochemistry. So here, so you can also in mechanochemistry, it's like a top-down approach. You can take a bulk material to break down to nano, but I did it differently. What I did is, I used the mechanochemistry to assist my reaction to happen in a bottom-top approach. So what I did here is, I did not add a bulk material, added starting material, and then I ball mill them in a different time and different RPM. I get a beautiful color of this cesium lead bromide nanoparticles. These look like a rod-like structure.
Please share your screen, sir, please.
Sorry?
Screen is not visible, sir.
Right. Is it not now?
No,
Not,
no, sir. Please share your
okay.
screen, sir.
Sorry. Let me save it. I can share it again then. Okay. Am I think I was stopped for sharing, or what's happened? Because I'm not able to share now. Oh yeah, okay, right, now I can. So, yep. Here is my presentation. Can you see now?
Yeah,
now it's
it
okay,
is, sir. Yes, sir.
Fine.
Yeah, okay, that's great. So yeah, so now, so if you see here, so you can play around in this chemical method. So what you can do is you can change the timing of ball milling, and you get a different shape or different nanostructures. As I said, like you have a nanorod type, and you have at 60 minutes at one hand, that's 3 hours. So you have a nanorod shape, but the aspect ratio has increased. The length of rod is increased, and also the diameter decreased. So yeah, so you can. There is a plenty of opportunity in this area as well. So it's basically it's a green synthesis, and industry can scale up. And you can obtain the range of tunable morphology and size as you want for the different application. So yeah, I mean, we fully characterize, we understand whether we have a pure or any impurity with the various characterization techniques. I don't want to go into detail, but what we understand is main important is to understand the band structure. As I said earlier, the selection criteria is very important. Whether the band structure has a suitable band gap, or the positions, the conduction and valency band position to happen the reaction, the reaction you chosen basically, whether it is a CO2 reduction or water splitting or degradation, any kind of reaction, or maybe a degradation of COVID. So yeah, and then we test them for the CO, particularly I've been focusing on CO2 reduction. As I see, like they are active, they are producing some carbon monoxide and carbon, methane as a product without using any kind of sacrificial agent, but the activity is very low. The activity is very, very low. So, yeah, so like how we can be improve the activity, I will go through a later slide. But what we can do is we can also play around with the ball size, not only time. For example, when you change the balls in the ball, if you change from 5 mm size to 15 mm size, you have a different aspect ratio of the nanorod. The size of the nanorod is, the diameter is same, but you are able to increase the aspect ratio. It's good for the charge separation. And similarly, you can see that activity. So if you compare these two activity, the high aspect ratio nanorod is showing much better activity than the pure. And then I also play around with the starting material, the precursor. For example, I picked one of them, a cesium precursor. When you use the cesium acetate, you have a nanorod structure. When you use the cesium bromide, you have a nanoseeds. So you can make a 2D nanomaterial using mechanochemistry. And again, so these in terms of total productivity is more or less same. So that maybe also the high surface area in case of 2D material, but the activity remains similar, because the reason is in 2D material, the charge recombination is quite high than 1D, because in one dimension, the electrons are more confined in one direction. So the charge separation is much higher. So yeah, so one of the key is, as I said, the stability. These pure cesium lead bromides, the perovskite nanocrystals are unstable. You can see the activity has dropped, and then you see the various other phases, and it started decomposing this material. But what I did is, So I combined with the graphene. So I embedded these nanoparticles into graphene seeds to improve the stability. And when characterized, we see nicely wrapped. You can see that, and we also loaded a bit of copper metal because the copper is something is less expensive than other metals like platinum and ruthenium, and it also more selective towards the CO2 products than the water reduction, because selectivity is important. And here you see the different photocatalysts. So you see when you have a nano seeds with copper and the graphene oxide, the activity is much higher than when you have just nano seed and RGO or pure or even copper or just copper RGO. It's much higher, even much higher than with the nano rad, because graphene is a two-dimensional, and these if you in case of two-dimensional perovskite structure, both are two-dimensional, you have a face-to-face interface. So it's the contact, along the interface is much higher in the case of nanorad, as I discussed earlier. So and then more interestingly, you see the reproducibility much higher than pure. Pure was not stable, but the composite is much stable and steadily reproducing it. So one of the important factor to understand this efficient the improvement in efficiency is the light absorption. So you're improving the light absorption across the spectrum because of the graphene and copper nanoparticles are plasmonic. So yeah, and you are able to separate the charge separation through the graphene layers, because graphene is a conductive layer, and then the electrons are trapped on copper where the reduction happens, and then there are OH groups, so you can't reduce completely graphene. You can, but it's very difficult. But the graphene we made here is we have some of the functional groups like hydroxy, so that is helping here to react with the whole and reduce the oxygen without using any sacrificial agent. That is great. And the quantum efficiency we achieved earlier, I said we only achieved the 0.26, but here it's 10 times higher than that. The quantum efficiency, the previous quantum efficiency. That's great. So with the span of 2 years, we came from 0.2 to 1.2. So, but it's a long way to go. It's still, as I first pointed out, the state of art. It's still a basic level or advanced research level. Yes, as I said, stability. So to understand the stability, we did some X-ray diffraction patterns. So you see that there is sintering is happening. We've been working on to improve because of the sintering, the particles or nanoparticles are agglomerating. You can see the full width half maxima is keep increasing. So, but yes, but there is no phase is absorbed like in the case of pure. So no decomposition is absorbed even after 8 days. So to understand the stability, we did some contact angle, because the reason we have a better stability is because of the bit of hydrophobic nature because of the graphene. You see the contact angle is, in case of nanoseed, it's 0, but it's not hydrophobic, I should say, but we improved the hydrophobicity. So basically in a reverse order. So that's why this is able to give a good stability. So another on what we did is to further we prepared the device to further what we did is the mesoporous carbon, and along with the graphene simple graphite sheet, we just coated with the graphite sheet, readily available graphite sheet. So that give us a much better stability in direct in water. It lasted for for hours and hours. So that is a record achievement in terms of stability on these materials, particularly in the literature so far. So this paper published in Nature Communication. And then we applied for the water splitting, the photoelectrochemical water splitting. So here, so as I said, like the anode is the oxidation is the bottleneck, because the kinetics are sluggish. It doesn't happen that as easy as happens the reduction, that is proton to hydrogen. So so that's why we use as an anode to oxidize water, and whereas on cathode, so you produce the hydrogen, so you can split the water into hydrogen and oxygen. And the Ricard-Faraday efficiency, that is the efficiency, the theoretical versus experimental. So that's very high. So that's great. So we've been working on scaling up this this process. Yes, so some of my papers have been cited in news outlines, various news outlines from postdoc, from in different, while I was in different universities, and also some of the, one of my PhD paper, which is done by, I'm always proud of it. I done this work from NIT Warangal, so it's been highly cited in, all-time highly cited in the journal. And my first paper is cited more than 500 times. And I wrote as Dr. Ram introduced, so I wrote several books, book chapters on CO2 and then other applications. If you are interested, please go through my file and read them. If you want a copy, let me know. It's confidential, but I can share with you. Yeah, and let me thank, these are the great personalities who has been inspiring and supporting throughout my research career. And not least, at last, thank you so much for your kind attention.
Yeah, thank you, Santosh.
Yeah, thank you.
You have given a wonderful talk on photocatalysis. So now this is the interaction time for. Now I request Dr. Ashok, in charge for the questionnaire.
Sir, thank you, sir. Yeah. Thank you, sir. I am Ashok Baswa, sir.
Right. Yeah.
Good afternoon. Good evening, sir. Sir, it is a very impressive talk on nanotechnology related to photosynthesis with your very crystal clear picture slides, sir. So it is very clear now. So on behalf of participants, we have some series of queries, sir. So the first question raised by Sushma. So this method be used to cleanse superfluously contaminated water that is infused with browny raw materials and dust particles?
Yeah, so I mean, it can be applied, but that I would not speculate more on this because there is not much literature available. So far, the literature available, or even I have done during some of work on water purification during PhD, is by picking up a pollutant, very well-known model pollutants like phenols or phenolic group compounds, dyes. But yet that is always a challenging working with the mix of impurities in real world application. But you can't, one cannot rule out, but yes, it's something people are working on it, and there are some industries also taking up. They are bringing into market, but that is only for selective compounds in industry. Certain industry produce certain compounds, so they want to eliminate them. They want to degrade them. So that perfectly works because you studied well. But the range of mixtures and the mixtures he was talking, it's something to understand. If not studied, or if you need to look at the literature, or if not studied, it's something to somebody has to take up and. Based on the requirement, the industry, if the industry is interested, yeah, it can be done.
Okay, sir. Another question raised by Dr. Padmavati, madam. Sir, could you please tell what happens to quantum size effect in case of insulators and semiconductors?
Insulator and semiconductor.
Yeah, quantum size effect.
Right. So. I don't think so. In insulator, you want to bring into, okay, if you, yeah. So, do you want to bring into like a nanoscale the insulating material, or?
Yeah, nanoscale quantum size effect only.
The quantum size effect only exists, so which has a semiconducting property. Yes, some of the insulators, if you bring them to semiconductor level, yes. And then yes, they behave as some of these insulator. They behave as a semiconductor, and then they conduct the electricity. So, but if you take any bulk insulator, but that doesn't, I mean, there's no quantum size effect exists, I would say. I hope so I answered her question.
Yeah. Another question from the same Padmavati Madam, sir. What are the efficient methods to characterize photocatalytic materials and nanomaterials?
So, sorry, can you repeat again?
What are the efficient methods to characterize photocatalytic materials and nanomaterials?
Right, nanomaterial and photocatalytic material.
Yes.
Yeah. So yeah, the best is like, I mean, it again depends on what you are looking at. For example, if I am looking at, for example, in what I am interested now, I've been making materials and characterizing with the various microscopy techniques like TEM and SEM. But what I'm interested in doing some in situ experiment to understand the mechanism, how does it happen? So in that case, what I go for, I don't go for the microscopy technique. I may, if in future any microscopy does, which allows the in situ measurement, but as of now, I don't think so. But I would I'm more interested in drift, you know, or ATR, attenuated reflection sampling. So that's where you can, you know, in situ, you can understand the species forming on the surface of catalyst, and that helps you to understand the mechanism, what pathway it is taking, you know. So then you can control the better the property at nanoscale to improve the selectivity towards a particular product.
Okay, sir. Thank you, sir. Another question from Swarupa, sir. How the band gap energy value will get increases or decreases during photocatalysis by doing composite or doping compared to parent nano compound?
During the catalysis.
Yeah. How the band gap energy value
right.
differ.
During the, I mean, I would say it should not change. If your material is robust, why should it change during the catalysis? Of course, it may. If your material is not robust, or if having some, there are having some chemical changes, or you are doping, or you're self-doping, or you are, you know, you are degrading, or you're forming something else, then the band gap may change. But otherwise, if you have a robust material, it should not change during the reaction.
Okay, sir. Another question from Dr. Haripadmasri, madam. What is the method used to integrate PiO2 and LDH with LDH? Is the structure of LDH intact? And what is the anion of the LDH taken?
Right. So I use the hydrothermal method. It's cobalt aluminum. Okay. We have a hydroxy groups in the layer. And then also, of course, you can't avoid the CO2 as well. So CO2 from the atmosphere, and that is what we want as well. We want to capture the CO2 and then convert into useful products.
Okay, sir. Another question from Anuradha. How can we choose a suitable dopant for a particular compounds to affect band gap energy?
Particular compound, yes. That again, like a particular photocatalyst, you mean, yeah?
Yeah, suitable dopant, yes.
A dopant, right. Yes. So it dopants, again, it depends on are you more interested in oxidizing water, or are you more interested in reducing water or CO2? Or if you are reducing, for example, in dye degradation, for example, if you dope with a metal, it absolutely works with dye degradation, because it can, you know, the electron from the trapped states, the electron can transfer into dye molecule. But when it comes to, like, for example, CO2 reduction, you can't dope metal and apply in CO2 reduction, because the electron cannot go from lower energy to again higher energy or captured by the CO2. There are challenges, but it depends on the application, what applications he wants to work. But I would, as pointed out in the beginning, I would advise to focus on like a P-type doping, you know, just above the valency band. P-type doping is suitable for photocatalytic application than N-type doping, and also I would advise more on focusing on surface modification than the doping, to be honest.
So property-related dopant should be taken, sir.
Yeah.
Is it? Yes. So another question from Amiya. Can quantum size effect will be same for the same material with different color? Can the nanoparticles of all the materials have different colors from their original colors? So related to color variation, sir.
Oh yeah, exactly. I mean, yes, of course, the different nanomaterials. I mean, when you say the different color materials have a different, I mean, uh, different color materials don't have a same band gap, but slightly, I mean, almost similar band gap. But it also depends other factors comes into picture, but slightly different, not exactly the same. But more or less, yes, of course, when you say semiconductors, then it is possible. Laws extend, so they have some similar color, but not 100% true. It
Yeah.
also depends on the other properties. And second question, what she asked regarding the
Yeah, can the nanoparticles of all the materials have different colors from their original colors?
Oh yes, exactly. So I mean, not nanomaterial to be honest. There is a confusion between the nanomaterials and because the quantum size only exists when you reduce the size of the particles to the double to their Bohr radius. So then in that case only the quantum size effect, and then there is a color change. Otherwise, it doesn't. If you make a titanium nanoparticles or bulk titania, if it doesn't take it to below like few nanometer, it doesn't change any color.
Related to gold color, sir, in the presence of any kind of light, can the nanoparticle of gold will show red color?
Sorry, repeat again.
In the presence of any kind of light, can
Right.
the nanoparticle of gold will show the red color?
Not all time. I mean, not really. So they absorb different light and reflect different. So because it depends on the reflectance, right? The color you see is because of the reflectance. So it depends on the light you are shining it.
Okay, sir. We have a couple of two questions, sir. One question from Anuradha. What are the factors that affect while taking anion or cationic dyes in photocatalysis of compound?
Effect of cation, yes, of course, the basicity or acidity, the pH matters. So yeah, and then it's a relative question. It's related. It depends on your catalyst, what kind of band structure you have. If you choose according to your band structure, if you adjust the pH, that can degrade your material. If you, for example, have a material that doesn't have enough band gap to produce at room temperature, so the OH radical produce OH radical at room temperature, then if you adjust the pH, that may produce the OH radical, then degrade. So the pH matters. Yes.
Okay, the last question, sir. Is there any top-down approach to synthesize exactly all same size nanoparticles?
It's a very tricky question. It's impossible, I would say, because it is material to material. You have a range of different properties. But yes, there are certain materials you can make with the same size. But yeah, but you need to adapt a different parameters to synthesize them. Not like in a same conditions you can produce the same size of different material.
Okay, sir. One more question I added now, sir. Sir, please could you explain us what is quantum confinement effect in simple words? How it is affect the behavior of material?
All right. So the quantum confinement effect simply like, as I said, like you have energy band gaps, right? So the energy levels, as quantum physics says, there are the electrons in the rotating around the nucleus in an orbital, and they don't have a certain space. So when you bring down to nano size, what does happen is these energy levels squeeze each other. The electron is not anymore free. The motion of the electron is restricted. So they create the band gap. And these materials have a great application, not only in photocatalysis, many other applications, solar cells, or even optical, light emitting devices.
Okay, sir. Thank you, Santosh sir, for your great patience towards questionnaire. So over to Upender sir.
Vijay sir, can you unmute?
Yeah.
Sir. Yeah, over to Vijay Kumar sir.
Yeah, okay. Thank you, Santosh. You have patiently given your answers to all the questions. So it is a very nice presentation. You have started from basics, what is photocatalysis and what is material and what is nanomaterial. So I hope that our participants enjoyed your lecture. So now this is the time to propose vote of thanks. Now I request Dr. P. Sarita Rajendra Madam to propose vote of thanks to our speaker. Over to you, Madam. Madam, can you hear me?
Ma'am, unmute me. Madam, unmute me. Unmute yourself. Unmute yourself.
Devendra sir.
Sir,
Devendra,
already I unmuted, sir. Madam is not
Madam
unmuted.
has to unmute.
Already I have done, sir.
Hello, can you hear me?
Yes, ma'am.
Yes, yes. Okay.
A very good evening, good evening to all of you. And we have had such a wonderful lecture, and I was totally, I can say, absorbed, not absorbed, totally into this lecture. So, on behalf of our college, our most valued, invited, young, dynamic Dr. Santosh has enlightened us with the topic of photocatalysis, which is very useful get an environment. So on behalf of various dignitaries, participants, researchers, students, it is my privilege to have this opportunity to propose a vote of thanks to Dr. Santosh. I extend a hearty vote of thanks one to Dr. for gracing the occasion and sharing his valuable moments. He has clearly correlated a very common principle that exists in nature, that is photosynthesis. And he has also told that by using a suitable material, different chemicals can be synthesized, such as methane, low carbon atoms, that is carbon monoxide, methanol, and these being very important raw materials in any industry, they become a feed to any industry. This is very, very important. And he has also spoken about choosing an ideal catalyst. So what he meant about ideal catalyst was he specifically talked about the volume and the surface area relationship and how any reaction would take place to result in better photostability, better suitable band alignment, and in low cost and by using non-toxic materials. He has also talked about not using very expensive materials such as platinum and ruthenium, which is very ideal anyway. And he has also talked about various materials like titanium oxide, cesium, or other UV active materials which can be used to use photocatalysis. And finally, in the end, I would just like to conclude, today, the whole world is moving towards developing a clean energy and clean environment. And developing fuels via artificial photosynthesis would be very, very beneficial to the whole world. Thank you, Dr. Santosh. I thought you were a very big person, but by just totally, so happy to see you meet such a dynamic person. I hope really would meet you personally when you come to Hyderabad. I would be very happy to do that. Thank you once.
Thank you so much, madam. Thanks for your kind words. So definitely, I will be visiting Nizam College definitely when I come back to India. That's for sure. Yeah, it's a pleasure always to talk to students and faculty members, friends, colleagues. Thanks a lot.
I'm happy to share with you is that myself and Santosh both are batchmates. Actually, we have done our MSc from Kakatiya University. And then after, when I was joined in NIT Warangal, he is doing his research there.
Exactly.
So very nice of you, Santosh.
Thank you so much for inviting as well. Special thanks to you.
Yeah, thank you.
Yes. I was thinking just for the students, your own students. I said yes, and then he said it's a webinar. Then I said okay, I did not say no to because yes, I gave a words. Then I wanted to.
yeah, thank you.
Thank you, Santosh sir, for your excellent narration and detailed focus on photocatalysis. Thanks a lot.
It's my pleasure, Upendra. Thanks a lot.
Yeah, now of course it is a virtual platform. Now, as a token of gratitude, we are sharing a certificate appreciation Dr. Santosh, please accept our appreciation certificate.
That's so kind. Thanks a lot.
So, can you see this?
Oh yeah. Thanks a lot.
Yeah, thank you very much.
Looks beautiful. My picture is good as well. Thanks.
You look so handsome.
Thanks a lot.
Thank you, Santosh. Once again, in future, definitely I will contact you.
Oh, definitely. Anytime. I'm always happy to talk.
We'll be in touch with you, sir.
Sure. Thanks a lot. Thank you so much. Thanks, both of you. Thanks.
Now,
sir.
Over to Upender, sir.
Yeah, good evening to one and all. And here we have completed today 2 sessions, one by Dr. Srinivas Anandan, sir, on lithium-ion batteries. And just now we have completed a session by Santosh Kumar, sir, on photocatalysis and relevant stuff. And tomorrow we're going to have 2 more lectures, very interesting lectures, one by Shivakumar, sir, from NIT Rourkela on photoluminescence, luminescent materials, and the second by Dr. Ashish Chaganlal Gandhi from Taiwan, which is completely different on magnetic materials and that relevant stuff, and which are very important materials in the advanced functional material point of view. So I request all the participants without miss kindly join us. And besides it, we have also very important validatory session by almost 10 to 15 minutes. And please be participate in that and grace the occasion. Yeah, over to Vijay Kumar, sir.
Yeah, thank you, sir. Thank you, Dr. Upender Garu. So now I might.
Sir, one more thing. I forgotten to convey my thanks. I would like to thank the Dr. Sakram sir, who head department Nizam Chemistry, Nizam College, and I must thank to Himabindu, who proposed word of thanks to one of the speakers. And my special thanks to Sarita Rajendran madam, who gave word of thanks to Santosh Kumar sir. And besides it, Ashok sir, especially I must thank Ashok Baswa sir, who have taken the very important questions of the participants to the speaker and get them answered. And even I thank Ashwini madam, who supported us to show appreciation certificate to earlier speaker. Thanks a lot. Yeah, Vijay Kumar sir.
Thank you, sir. Thank you, one and all.
Yeah, Devendra sir.
Yeah, yes, sir. I'm closing the session, sir.
Yes.
Feedback form already you posted. No?
Yeah, we already posted feedback form, and of course we do post in WhatsApp group. Please respond to it.
It is done, sir.
Yes, right. And we'll be signing off today.